Okay, thank you, Professor Pritam, for such a wonderful introduction to me. Actually, so today I am going to talk about molecular dynamics simulation of manufacturing process. Actually, so why this topic I am highlighting? Because if you see in the field of manufacturing, uh, when I was doing my bachelor's, actually, in manufacturing only a single textbook was there, and there were very limited modeling and simulation parts were there, actually. So if there is very limited science and modeling is there, then people gets very limited knowledge, actually. Huh. So and because of that, development doesn't comes further, actually. And second thing, uh, people also don't get insight about the process detail. So interest and future development doesn't happen. So this is why I'm telling, within our country, I'm not seeing the people in manufacturing sites who is doing extensively in modeling and simulation. More of the researchers are uh, uh, directed towards experimental study only. The moment you will keep doing experiments, you will not able to find out new physics, new phenomena, actually. Huh? For that, we have to go beyond experiments, actually. So this is why I am putting molecular dynamics simulation. So in my presentation, I'll also give some flavors about other modeling and simulation attributes. So here in this slide, you can see from the left, actually. So left, there is some atoms, some molecules are there, which needs to be modeled at a very small scale, maybe at atomic scale. Then after that, I have given some little bigger picture, actually. Bigger picture means number of more atoms are more, actually. So again, the domain of modeling is different, actually. And thereafter, the result comes, actually, like the forces are computed. So what I'm telling, keep from atomic scale, you can able to find out some parameters can be suitable for higher uh, uh, higher scale of modeling, a special scale of modeling, and then that can be used to compute actual outcome. Outcome may be in form of vibration, force, temperature, whatever we need, actually. And by this way, we can able to quantify the process outcome, actually. And meanwhile, we can also see the dynamics, how dynamics is taking place, so that the process understanding can become clear and clear, actually. So now this is the outline of my presentation. Here I'll be discussing about introduction of modeling of manufacturing process, how we can model a manufacturing process for molecular dynamics point of view. Then why MD simulation is required, molecular dynamics simulation, why it is required. And I'll also give some glimpse about the types of MD simulation which can be used for molecular manufacturing uh, domain, actually. Then I'll give one case study in super finishing, that is CMMRF process. So in CMRF process, I have implemented some uh, molecular dynamic simulation modeling as well as classical modeling. So those things I can present, I'll present in CMRF process. Then I'll talk about a scope for other process, actually. Because there are many type of manufacturing process which needs MD simulation and other process, so that their understanding and uh, their process capability can be enhanced, actually. And finally, I'll conclude at the last, actually. Yeah, this is a typical time and length frame I have given for various types of problem related things. Like if you see the time scale, it is starting at the ordinate side, actually. That is 1 femtosecond. It is going up to few hours, actually. And at the abscissa, the length scale is going from few angstrom to few meters. So when this time and space, like very small time and very small space, like 1 femtosecond and 1 angstrom is concerned, then quantum chemical simulation comes into picture, actually, where atomic interaction has to be done through uh, Schrodinger wave equations, actually, on which electron to electron interaction can be carried out actually. Afterwards, when we'll come to nanometer domain, actually means some tens of angstrom value, means cluster of atoms are there actually. So there, the quantum simulation cannot be done, because this quantum simulation with few atoms is quite possible, but it is very computationally it is very extensive actually. So if we'll go to more than 30, 40, 50 or 100 atoms, then this quantum chemical calculation cannot be possible in present computation facilities actually. So for that, molecular dynamics simulation can be implemented. So here I have put two types of molecular dynamics. One is reactive molecular dynamics, and the next one is a classical molecular dynamics simulation. So reactive molecular dynamics simulation means chemical exchange can be modeled actually. That what chemical exchange is taking place. So that can be modeled by reactive MD simulation. And obviously, since chemical reactivity is being studied by this reactive MDS, so it will again take more time, and it will be computationally more intensive. So it will again not take more atoms. If you like, if you go to more than 500, 600 atoms, then the simulation time will be very, very slow. So in that case, what we can do, wherever a chemical interaction is there, those portion reactive MDS can be applied, and other portion will be with classical MDS. So in classical MDS, it is simply interatomic pair potential. Like I think yesterday, one of my friend, Dr. Anu Sharma would have presented the MD simulation for nano scale cutting. So there he would have explained how classical MD interatomic potential plays an important role actually. So in classical MD simulation, the interatomic potential is being used to create interaction between uh, uh, two and more atoms actually. And afterwards, the mesoscale modeling comes actually. So in mesoscale modeling, uh, dislocation dynamics study can be done. And at the last, finite element analysis. So finite element analysis will not include atomic or micro scale phenomena. It will only include uh, a classical phenomena actually. So here I have categorized ki, uh, how different type of modeling can be used for different application. Like if we'll if I'll come from the right to left actually. So right, AFA simulation can be done to study some like in case of uh, in some sort of magnetic fluid. So magnetic field and magnetic force can be studied by AFA simulation. Then further, the magnetic force can be converted into the polishing force, and the polishing force can be used to apply the abrasion force through classical MD simulation. Then chemical reaction between abrasive particle workpiece and the slurry can be studied through reactive MD simulation. Then within the chemical, how uh, how new species is getting formed. So that can be studied by quantum scale simulation actually. Now, why MD simulation? So here, uh, if you'll see any manufacturing process, experiment cannot do for very high spatial and temporal resolution. Like in earlier slide, I showed the quantum scale MD simulation, you can have the time scale of the order of few femtosecond actually. In fact, the classical and classical molecular dynamics simulation, the time scale can be few femtosecond or higher actually. So with that higher temporal resolution, we don't have any experimental facility to study any manufacturing process with very high temporal resolution and a spatial resolution as well. If you'll see a spatial resolution like atomic force microscopy, then scanning electron microscopy, and STM scanning tunneling microscopy. So these are a tool by which we can characterize the samples where the spatial resolution will be few angstrom or few nanometer, but the temporal resolution cannot be maintained. So when we want to study any process dynamics, temporal resolution as well as spatial resolution, both are required at very high level actually. So for this, only MD simulation finds suitability actually, other than other experimental or any modeling tools actually. So this is why MD simulation has become popular for studying or simulating manufacturing process. Then if you will see further, I can also explain. Suppose if I have some material and I don't know their Young's modulus of elasticity or boiling point or thermal conductivity. So those things can be computed through quantum scale MD simulation actually, or a classical MD simulation. So the parameters for macro scale modeling can also be evaluated. For example, I can give an example like some flammable material like magnesium, zirconium, uh, uh, or some exotic material which cannot be directly experimented without uh, without any protection. Like if you'll handle some radioactive material, so nobody will allow to take extensive experiment to find out the microscopic properties like Young's modulus, tensile strength, hardness. So those things can be computed by using molecular dynamic simulation. Then towards development of new materials, like if you'll see graphite, diamond, and CNT, all three belongs to carbon group only, but their structures are different actually. Like in case of diamond, the structure is tetrahedral structure. So the tetrahedral structure has given a very high strength. In case of CNT, uh, the graphite shape is turned in circular fashion, so it has enhanced the strength further actually. So by MD simulation, we can study what structure will give the required properties actually, and we can aim to make that structure actually by experimental means. So here MD simulation can be used to predict the new material for our present requirement actually, and we can start aiming towards fabrication. Then in case of any process, including manufacturing process, when we conduct molecular dynamics simulation, we study how material movement is taking place at atomic scale. So their mechanism of process can be studied, and it can be quantified or qualified actually in terms of new models or new phenomena. Like all of us know, as size comes down, the size effect gets dominated, and the new size effect phenomena comes into picture, which violates the conventional continuum phenomena actually. So and if you don't model any process at nanometric scale, then we will not come to know what phenomena is taking place. And then this is why MD simulation is required to understand science and mechanism of process at nanometric scale or micrometric scale actually. Now if we come to the type of MD simulation, so as earlier I told, the first type is quantum chemical molecular dynamic simulation, that is also known as ab initio molecular dynamic simulation. Ab initio means it is a starting of molecular dynamic simulation. So what they are doing in ab initio molecular dynamic simulation, the Schrodinger wave equation is being solved between atoms actually. So all electron wave function using Hamiltonian operator are being solved using proper approximation technique, and there are various types of approximation technique like density functional theory, then Fortry-Hart theory. So there are many techniques to solve Schrodinger wave equations. So those techniques can be used to study the interaction between two atoms or more atoms actually. And this study will help to find out the interatomic potential. like when two atoms is coming closer, then how energy is going up. And the moment you'll quantify energy versus distance, then this can be used for data training to find out the function for potential energy well actually. And thereafter this classical molecular dynamics simulation comes into picture. So classical molecular dynamics simulation, they are using interatomic potential, which can be quantified by experimental means or by using the earlier ab initio molecular dynamics simulation. So the moment we have interatomic potential, we can conduct classical MD simulation. I'll show how classical MD simulation we can take start actually. Then I have put one more thing, reactive molecular dynamics simulation. When a manufacturing process is not comprising any chemical reaction, then we need not to put reactive molecular dynamics simulation, because reactive molecular dynamics simulation includes interatomic potential in form of chemical reaction as well. Like when two atoms comes into closure, then what kind of new species will get formed. So these information are also stored in reactive molecular dynamics simulation actually. So but what will happen if you are solving any mm, uh, any process with a very large number of information, then their computation will be effort will be very high actually, and our simulation will be very slow. So this is why we avoid using reactive molecular dynamics simulation when the process is highly mechanical process actually. But when some sort of chemical interaction is also taking place, then obviously reactive MD simulation is essentially required. So that what kind of chemical reaction is taking place, what new species will get formed. So those things can be analyzed by using reactive molecular dynamics simulation. Now, when we start any MD simulation, these are the steps for initiating MD simulation. So here the first step is material building. So we have to build the material like our workpiece, then polishing media or cutting tool. So their geometry has to be constructed. Then inside the geometry, the atoms has to be created. Then once atoms are placed within the geometry, then pair interaction between atoms have to be created actually. What kind of pair potentially we want to create? Like if workpiece is metal, then embedded atom method pair potential can be applied. And if workpiece is some sort of covalent bond kind of things actually, like diamond or silicon or quartz, then in that case a touch of kind of interatomic potential can be applied. Then interaction between abrasive or tool and workpiece, between two body interaction. Then whether reactive is required or mechanical interaction is required. So accordingly, the interatomic potential can be selected. Then boundary condition. So boundary condition means uh, it is similar to the finite element analysis. Where you want to uh, uh, fix the material, and where you want to apply force or movement. So those things can be applied. And in some case, if there is some symmetricity boundary conditions, so periodic boundary condition can be applied so that larger domain can be modeled actually. Then after applying the boundary condition, the atom initialization has to be done. So this will be done randomly in MD simulation, where initial position and their velocity will be randomly put based on the initial geometry and the temperature of the components. So once it is initialized, then after initializing, the atoms of all materials will not be in equilibrium condition. It means their equilibrium position is somewhere else actually. So in that case, what will happen? The system means the all atoms will have very high potential energy or cohesive energy. So it will likely to becomes unstabilized while modeling this system actually. So equilibration comes into picture. So in equilibration, what we do? We try to stabilize the atoms. So this stabilizing can be done by various way. So one can be done by reducing the temperature. So while equilibration, the lowest temperature can be set like 0 Kelvin or 10 Kelvin, and then the temperature can be ramped up to room temperature, and there it can put for maybe few nanosecond to see how potential energy of entire system is uh, uh, coming actually. Means if potential energy not fluctuating, it has become almost constant, then we can assume it has the equilibration has been achieved. And meanwhile, we can also compute the cohesive energy, and we can compute at this lattice whether cohesive energy is matching in case of a stable lattice or not actually. So that will also give a fair idea equilibration is done. Then afterwards, the process parameter will be applied, like finishing force, cutting force, temperature. So all external process parameter can be applied. And when we'll apply the process parameter, it will start uh, uh, start doing the movement of atoms actually, and due to that, the interaction takes place, and new shape or new new things will start evolving. Like if some chips is getting formed, then chips formation or some debris formation or some new chemical species generation will start taking place. So those things will start coming, and that can be stored inside the memory of the computer. And afterwards, those data, whatever we have stored, can be used for post processing actually. So in the post processing, we can able to visualize the result, and we can also uh, after visualizing, we can also quantify the output as per our requirement actually. So this is the basic governing equation for classical MD simulation. So the governing equation is Newton's second law of motion actually. So this is force is equal to ma, and the force is negative derivative, different positional derivative with the interatomic potential, and this interatomic potential V is can be bonded or it can be non-bonded actually. Means it's chemically bonded or non-bonded. Then along with this governing equation, the Verlet algorithm is also used. So there are two Verlet algorithm. One is displacement Verlet and second is velocity Verlet. So these algorithm are being used to find out the position and velocity of atoms actually. So here I have again presented the flow chart, how MDS can be taken actually, right from a start. Like here I can zoom and show actually the same way. Whatever I spoke earlier, that initially while starting, what we can do. 1 minute. While starting, we'll specify unit for the simulation. What unit we are using. There are maybe I think 6-7 units in present MD simulation method actually, like real units or metallic units or SI unit or LJ units. So those units can be taken. Then dimension of the system has to be specified. Types of boundaries. Then atom style, what atom style we are going to use. Then neighbor condition. Neighbor condition will basically indicate about the interaction with the neighbor atoms actually. Then after that, the geometry building and this atom creation. The moment geometry building and atom creation is done, then grouping has to be done actually. So grouping is required. Suppose if I want to apply some boundary conditions like cutting force and all actually, or some local temperature has to be given. So that local grouping will be done, and within that group, that temperature or force will be applied. So uh, because of that, grouping is essentially required when we are doing MD simulation. Then input data potential in form of potential function, that is interatomic potential function. Then we have to assign interatomic pair potential and their coefficient, then equilibration, and finally we'll calculate the potential energy of the entire system, and we'll see uh, whether potential energy has become stabilized or not, so that we can ensure how much change in potential energy is coming from the previous step to the next step. If it is within 1%, then we can say it is stabilized. Otherwise, we have to keep doing the equilibration actually, unless we will not get potential energy variation within 1% band actually. After that, the all constant like dynamics and forces, temperature, displacement of the process will be applied as a boundary condition, and ensemble will be a statistical ensemble will be applied. It depends upon the process kind of thing actually. Like if temperature is not controlled inside, then NV ensemble will be applied. NV means number of atoms will be fixed, volume of the system will be fixed, and energy will be fixed. Sorry. And after that, the computation will be done, and all data will be stored, and the post processing will do analysis and documentation. So in the post processing processing, all the computation like material removal, finishing force, temperature, stresses, everything we can able to quantify during post processing or analysis time actually. Now here I'll give a case study how MD simulation I have used in a case of CMMRF process. So CMRF process is a super finishing process that I have developed by combining two different processes. One is chemo-mechanical polishing process and another is magnetorheological finishing process. So the CMRF is a simple process actually that you can see from this schematic. So here you can see S and N. So the left side S and N is the magnet actually. This magnet is properly packed in a spindle. So spindle is rotating, so magnet is also rotating. And beneath of the magnet, there is a insulating or magnetically insulating layer. And just below the layer, a magnetic fluid, that is MR fluid I have written. Magnetorheological fluid is placed actually. So what happens when any magnetic fluid is put just below of the magnet, so it will become, it gets stiffened and it will form a pad or brush actually. And this brush this brush applies pressure against the workpiece. So you can see there is a workpiece. So workpiece is getting pressure from the MR fluid, and the workpiece is also submerged in a slurry, chemical slurry actually. So chemical slurry, what it is doing, it is chemically reacting the workpiece, and the chemically reacted workpiece is getting removed by using abrasion of MR fluid actually. So here the tool means magnet is rotating, means our MR fluid is rotating. So due to rotation, it is abrading, and workpiece having feed actually. So because of the feed, the rotation is getting averaged out over the entire surface. So material removal is taking place on entire work surface actually. And by adjusting the gap, working gap, we can able to control the polishing pressure. Means pressure, polishing pressure means the abrasion pressure due to MR fluid on the workpiece. So this process I have tried to model using MD simulation. So this is a schematic which shows the part to be modeled and studied. Like you can see near the magnet actually in the actual schematic. So in the magnet and MR fluid, I have just dotted, I put a dotted line that this zone needs finite element analysis and CFD simulation. So why finite element analysis I have put actually? Because magnetic field and magnetic force. Because the sorry, the MR fluid is applying pressure through magnetic force actually. So magnetic force have to be computed. So that magnetic force I'm computing using FEA simulation, finite element analysis simulation, and then magnetic force is getting converted into the polishing pressure. So CFD is taking place so that we can compute how much pressure is coming on the workpiece. Now, if we come to the workpiece and MR fluid interface, so there I have shown in on the surface of workpiece, you can see the middle left side picture. I have shown the abrasive particle, yellow. Uh, this yellow dots represents abrasive atoms of abrasive particles, and this green dots represents workpiece atoms, and then red, blue indicates the chip formation. So it shows when abrasive particle gets pressed by MR fluid, it will start abrading the workpiece. So their atomic interaction will take place, or nanometric scale interaction will take place. So their sorry, their MD simulation is required. Then on the right side, if you'll see the slurry tank actually. So in the slurry, there are some chemical, some magnetic particle, abrasive particles actually. So it will start sedimenting. So their physical stability or physical property needs to be controlled or needs to be monitored or studied. For that, I have done DFT, that is density functional theory, towards quantum scale chemical simulation. So that helps to study the chemical attributes of the slurry part actually. So now here, this I'm showing by modeling the CMRA process. I modeled, I understood what phenomena is taking place. Then I applied on silicon substrate. So on the left side picture, you can see this initial silicon substrate, which was having surface finish of the order of 1.3 micron. And when CMRA process was applied, then surface finish has become few angstrom actually. So because of getting very high surface finish, the surface has become reflective actually. So the quality difference is showing, but we don't know what mechanism is taking place. So this is why I'll start doing what process study I have done actually. So as I told, in case of slurry, I have to do a chemical study, and there is some abrasive particles, some magnetic particles. So we have to see whether it will become stable or not actually. Stable means abrasive particle or the magnetic particle is likely to get sedimented actually, because they are solid particle, and the slurry is having some chemical which is liquid phase actually. So solid will start sedimenting. So here I have taken 3 different fluids actually, fluid 1, fluid 2, fluid 3. So fluid 1, 2, 3, on which iron particle concentration is varying actually, it is decreasing. And in the fluid, the iron particle is modeled in such a way that it will have few forces. One is gravitational force, buoyancy force, then interatomic force between iron particle and the chemical layer, then the last viscous force actually. So when I modeled actually, you can see the left side image actually at t is equal to 0, it will be properly dispersed actually. And as time progresses, it starts sedimenting. Like in case of 500 seconds, most of the atom has, most of the this particle have come down, and at 1500 seconds, almost 70-80% particle are sedimented. So on the right bottom side, I am showing the quantified figure by both simulated CFD results as well as experimental value. So dots are experimental value and line is CFD results actually. So it shows how sedimentation is taking place. So there are 2 zones. So initially it will have very fast sedimentation, and afterwards there will be very slow sedimentation. So up to 80% sedimentation, it will happen quickly. So once sedimentation is taking place very quickly, means let us say within a few minutes, then we will not able to send the solid particles or abrasive particle or magnetic particle from slurry to the finishing zone or the polishing zone actually. So how we can able to uh, conduct the experiment actually. So for that, what I have done, I have put one surfactant actually. That surfactant is sodium stearate. So sodium stearate was used as a surfactant, and then I applied density functional theory, that is ab initio quantum scale modeling actually. So there, what I did, I I have varied the distance between iron particle atom and sodium stearate atoms actually. So you can see, I'll zoom the pictures actually, like here. Initially, you can see at the top side that iron oxide, FeOH, FeOH actually. So this is iron oxide, because what happens when iron particle is there, the external surface will get hydroxide actually. So iron hydroxide will get formed, and then this I am putting proximity with sodium stearate. Sodium stearate, there will be sodium Na atom, oxygen atom, then carbon hydrogen chain. This is hydrocarbon chain actually. And when I'm just bringing together actually iron atom and the sodium atom, if I'll bring together, then what will happen? In the next, you can see H and O, H of iron and O of sodium stearate is creating one yellow dotted hydrogen bond. So this hydrogen bonding is taking place. But here, if you see in this figure, the change in energy, and the bottom is interatomic distance. So as distance coming down from the right side, the energy is also coming down. It means the reaction or interaction is a spontaneous interaction. So here hydrogen formation is taking place, which is spontaneously happening actually. Yeah. And it doesn't require, it means when we'll put sodium stearate on iron particle, it will form hydrogen bond. But hydrogen bonds are weak bond. It will not help to physically stabilize the dispersion actually. If mass is higher, then it will break the hydrogen bond and it will again start sedimenting. Then what I did, I moved iron atom further towards the sodium atom. So you can see at the middle photo. Then further, it was brought closer actually. So what happens? It requires some energy to be crossed actually. Like you can see at the middle only, like bond breaking is possible when we'll apply temperature above 80 degree. So why I have written above 80 degree? Because if you see the minimum the energy difference for the activation energy, it is coming of the order of almost zero. 0.2 electron volt actually. So 0.2 electron volt is somehow similar to 80 degrees centigrade. So if I'll apply little higher temperature, so due to the atomic vibration, the proximity between sodium and iron will become more closer actually, and that will start breaking bond of the parent sodium and parent sodium with oxygen in sodium stearate molecule actually. So you can see the second left figure, that sodium atom is getting detached from the iron atom, huh? And afterwards energy has fallen down drastically actually. Means means the entire species is getting highly unstabilized, and unstabilized means some nascent atoms is getting formed, and a species highly energetic species are getting formed. So it will like to interact quickly so that their energy will get stabilized, and the minimum energy criteria can be achieved. So this is why the energy has come down drastically, and it is forming while decreasing the energy, it is forming ionic bond actually. So here you can see the ionic formation bond is taking place between iron atom and oxygen atom of sodium stearate. So here you can see the sodium stearate atom, oxygen is getting attached with the iron atom, and sodium is detached actually. So it means what happens when we will mix sodium stearate with iron, and if we'll heat up at 80 degrees centigrade, so sodium atom will get dissociated or get dislodged, and iron will make an ionic bond with the uh, sodium stearate molecule actually. And this sodium stearate molecule it's a little longer chain actually, so it acts as a coating surface actually. So this work was published in Journal of Micro Manufacturing, and there it was reported that with the help of sodium stearate nano coating, the sedimentation was improved from 15 minutes to a few hours, so actually 8 hours and more actually.
So what happens when we'll apply sodium acetate on our chemical slurry, then our iron atom will not get sediment because of formation of this coating of the sodium acetate molecule. So now in picture I am showing how CMRF slurry was synthesized. So for synthesis of the CMRF slurry, I have used CIP, which carbonyl iron particle, that is iron particle basically. Fumed silica is abrasive particle. Then poly, this is propylene glycerol (PPG). Then sodium stearate and water. So sodium stearate. So here you can see fumed silica is abrasive. Then PPG is additive, and sodium stearate I'm using as a surfactant for nano coating on the CIP particle, iron particle actually. And water is a main media. So you can see in the first left figure that the mixture was made and it was heated more than 80 degrees centigrade, and then this slurry was put under magnetic field. So you can see after magnetization what happened, it is forming a polishing brush or magnetic brush. Okay, and it looks very stiff brush actually. And after demagnetization what happened, again it has taken a slurry form actually. And then you can see their microscopic image at 475 times of magnification. Then all particle fluid dispersion is uniform actually. So it indicates there is homogeneous distribution of iron particle. It means iron particle is not getting agglomerated or it will not get sedimented actually. So thus reversibility aspect and life of the fluid can be very high actually. So in case of magnetic polishing, the water-based MR fluid synthesis was one of the major challenge. So that can be overcome by using this kind of nano coating techniques actually. So now when we'll come to the polishing zone actually where finishing is taking place. So I told I'm using a permanent magnet. Then beneath of the magnet on the left figure you can see the permanent magnet. Then one non-magnetic material. Then at the bottom MR magnetic fluids are put actually. So this entire domain was magnetically modeled, and I found out the magnetic. I'll not go in detail actually because our main concern is about MD simulation. So here by solving Gauss law of magnetism and Navier-Stokes equation, we can able to quantify the polishing pressure actually. So as on the right side figure you can see, as working gap varies, the polishing pressure will be different. So here I have shown Z is equal to 0, means working gap is 0, and as Z increases, the working gap increases, then we can get the corresponding polishing pressure. So this is the polishing pressure which was derived from the FEA-CFD integrated simulation, and it shows how polishing pressure is radially getting distributed. And on the right side photograph, it is showing the characteristic of the polishing pressure with different working gap actually. So it is showing two different zones, zone 1 and zone 2. So zone 1 is very sensitive to the working gap, means in 1 millimeter the change in polishing pressure is 5 megapascal. But in case of right side, the sensitivity is very less, means 1 millimeter change in gap yielding 50 kilopascal pressure only. So these two zone is helpful ki which zone we can operate actually. Like if you are using very hard material, then obviously we can go for zone 1. When we are using soft material, then better to go by zone 2 actually. Because what happened ki when we are going very hard, if you are working in zone 1, then a very large this thing will come actually. Large pressure will come, and by a small changing in working gap, uh, a small change in working gap, the pressure building will be very high actually. So again, zone 1 requires very high precision machine actually, but zone 2 doesn't require high precision because it is not very much sensitive to gap actually. It means if tool has some axial run out, so it will take care, because the change in polishing pressure will be within few kilopascal only. So here from this what we found out that this behavior is suitable for an ideal magnetic fluid, this whatever behavior we have computed is for ideal fluid, and the fluid will be physically stable actually. If it is not stable, then this behavior will not come. Now that polishing pressure I have converted into force actually. So using the cross-section area of the magnetic particle and the pressure, we can find out the maximum force. So in the table I have put at different working gap what can be force actually. So here I am getting force in terms of few tens of nanonewton to few thousands of nanonewton actually. And I have put two different type of model in the top actually. You can see the left side. I am presenting about mechanical finishing. So here you can see the uh, 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 material actually. The bottom is boundary layer, then thermostat layer. So boundary layer is fixed actually, where movement of atom is zero. Then thermostat layer on which temperature is frozen, means 300 degrees centigrade is fixed actually. Huh? Then afterwards, this Newtonian atom comes into picture for the workpiece. Newtonian atoms means temperature constant is not given. So temperature will vary depending upon the how much external energy or external work we are applying. Hmm. But obviously, this temperature will start getting conducted away using thermostat layer actually. So this is why thermostat layer is given. Otherwise, what will happen? The temperature will keep going further, and entire system will get dissociated and will not able to solve the problem. But in actual practice, what happens? Our workpiece is submerged in water actually, or slurry, whose temperature is at room temperature. So this is why thermostat layer concept was given here. And one asperity is also given. So asperity I have given to mimic the roughness attribute of the workpiece actually. And abrasive particle with the size, you can see white dotted spherical part actually, that is abrasive particle, which will have Fz and Fx. Fz means vertical force due to polishing pressure, and Fx means force due to the uh, 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 radial or lateral stiffness actually, stiffness of the magnetic fluid. Then on the right side, I have put how chemical attributes will be modeled actually. So again, same, the bottom of the right atoms are starting from fixed atom, thermostat atom, Newtonian atom. Then above the Newtonian atom, we have put chemical species. So in chemical species, you can see H2O, where O is representing in a yellow color, and others are oxygen. So H2O molecule. Then the chemical species, like if I'm conducting some alkaline media, so potassium hydroxide, so KOH. Huh? So like pink color is potassium, oxygen is yellow, and another is hydrogen. So KOH chemical species are put actually. So by modeling all chemical species on the top, we can uh, start the simulation, and we can see how chemical reaction is taking place actually. So here, the entire MD simulation, you can see, I have categorized in three different parts actually. One in aluminium. Aluminium I have taken so that we can understand how this polishing is taking place in case of ductile material. So this is why aluminium is taken. In case of ductile material, what is the main mechanism of the material removal actually? Then another material I have taken silicon. Silicon is brittle material, so I don't know how it will be taking place. So silicon was selected to study the process mechanism on in case of brittle material. Then at the last, I have used also SS304L. This SS304L is ductile material, but it is extensively being used in industry, and SS also requires some sort of nano finishing. So this is why I thought let us also go for this ductile material as well. And this material has multiple alloying elements, so effect of alloying element can also be studied actually. So now types of MD simulation. What type of MD simulation I have applied actually? So in first, I have applied classical MD simulation for mechanical finishing. Mechanical finishing means I'm simply doing mechanical abrasion. There is no chemical interaction will be taking place. No new chemical species will get formed. Huh? Only mechanical abrasion, like when abrasive is hitting, then how it will impact on metallurgical attributes, how it will impact on temperature, how it will impact on metal removal. Huh? So for that, interatomic pair potential was used without having information of chemical interaction. So this is done on all three material, aluminum, silicon, and stainless steel. Then in second, I have done a reactive MD simulation to understand how chemical reaction is taking place on aluminum and silicon. That is for chemical reaction only, like what I have shown on the right side, the right top figure. When if I'll put some chemical, then how chemical reaction and how fast, and how whether it's getting passive layer or it is getting corrosive layer. So those things can be studied by doing chemical reaction through reactive MD simulation. Then in the third, I have done reactive MD simulation using chemical assisted mechanical finishing. CAMF. CAMF means chemical assisted mechanical finishing. Means chemically I am reacting and then mechanical finishing is taking place. Means it is chemical assisted. Means chemical is assisting for mechanical abrasion. So here chemical and mechanical both is taking place. So this I have applied on aluminum as well as silicon. Then I have done classical MDS for on case of stainless steel as well. Then reactive part on chemical reaction is not applied on SS304L because of non-availability of uh, this reactive for potential file on stainless steel actually. Now here I'll show in case of stainless steel how sorry, how mechanical and chemical uh, uh, finishing is taking place. So I'll show one animation actually. 1 minute. Yeah, this one. So you can see at the top left side, it is chemically inert abrasive. It's abrasive and workpiece. Workpiece is stainless steel 304L actually. So here the red dots represents iron atom. Then orange dots represents chromium, and blue represents nickel actually. So this is SS304L LY actually, and it is interacting with the abrasive. So spherical component is abrasive, and the interaction potential is not having information of any chemical attributes. Means here there is no chemical interaction is taking place. So this is possible when we are abrading stainless steel with silicon abrasives. So silicon to SS interaction, there is no chemical interaction. And on the right side, the chemical interaction, it's chemically reactive because abrasive is silicon oxide actually, fumed silica. So this fumed silica is chemically reactive. So here you can see in the animation, you can see it is simply deforming actually. It has simply, you can see abrasive has deformed the workpiece and it has moved away. And material removal is not significantly taking place. It is simply deforming on the workpiece only. But in case of chemically reactive abrasive, what happens? You can see on the right side, this abrasive is getting attached with the workpiece, and the abrasive will take away the chips actually. See, it has taken away, chips is taken away actually. So material removal, a very good amount of material removal is taking place. And at the bottom, you can see the finishing force, how finishing force is coming. When abrasive is touching, then there will be rise of the force. And as abrasive moves away, then the force comes down. And with the gap actually, gap means working gap on CMR process, what I showed earlier, gap I have put
0 mm, 0.5, this 0 nanometer, 0.5 nanometer. So different location of the abrasive, how the force is varying actually. Then on the right side, temperature again. In case of a larger depth of penetration of the abrasive particle will have higher temperature, and in case of a smaller depth will have lesser temperature rise actually. Now I'll come to this slide. Okay. So now I will come to mechanical finishing. So in mechanical finishing, what we have found, the stress, the virial stress is computed and it is converted to von Mises stress, and you can see on the abrasive particle and workpiece. So a spherical is abrasive particle where stress is going up to 240 gigapascal, and in workpiece it is going up to 30 gigapascal in case of stainless steel. And similarly, we are getting the stress 10 gigapascal in aluminium, 38 gigapascal in stainless steel. So if you see these stresses, so this is somehow matching with this equation. I have correlated one equation. Fz is equal to Ce to E by 2 pi into 2 pi HR. So where C depends on the shape of the peak or surface roughness. E is Young's modulus. E by 2 pi is the theoretical strength of the material actually. Then another is geometry of the abrasive particle, and H is the indentation depth. So you can see on the plot actually, as the depth of mechanical abrasion increases, the indentation force increases actually. So this MDS data, it's somehow matching with this result actually. So it confirms that maximum stress goes up to the theoretical stress. There is also phase transformation that I'll explain later on actually. I'll show in some MDS result actually. Then it forms a scratch actually, like in mechanical abrasion, as I showed, the abrasive will apply pressure and it mechanically presses the workpiece, but it doesn't take away the workpiece. So it leads to the scratch formation. And this scratch will be chemically unstable. So it will lead to the temperature rise. As I showed, temperature rise was taking place. So that will lead to the temperature rise. Then abrasive degradation. So abrasive will also degraded in form of chipping and loading of the workpiece actually. So now here I'll show reactive MD simulation actually. 1 minute. So for reactive MD simulation, I have one more animation. So this one I'll show you. Yeah, here you can see MD simulation for CMR I have done for chemical reaction as well as mechanical interaction. So here you can see how abrasive particle is interacting with workpiece, and the chemical species of the slurry is also chemically reacting actually. So there you can see the abrasive, the top left side is the abrasive actually, and the bottom side is the workpiece, and in between there is a chemical species. So a chemical species is potassium hydroxide and water H2O molecule. So those you can able to see clearly. Now here you can see as abrasive particle coming towards the workpiece, you can see the bond between abrasive and workpiece is taking place, and while moving actually the abrasive particle, it was going like here you can see, as it is moving further, it started getting rolling. Why it started getting rolling? Because the abrasive particle and workpiece is getting bonded due to the chemical reaction actually. So it is not allowing to move in lateral direction. So that is forcing to roll actually instead of translation. So it is rolling now. And due to rolling, you can see from the back side, the atoms of the workpiece is getting dislodged actually, and the bond strength between abrasive particle and the dislodged atoms is much stronger. So the material is getting taken by the abrasive particle itself. So that here you can see. Now, in the same, if you'll see, is a phase transformation actually. Huh? So how the metallurgical difference will come into picture actually. So this here I'll show actually. So here, this is a workpiece green dots actually. This indicates FCC lattice structure actually. So in case of FCC lattice structure, as abrasive approaches, then this lattice structure is getting modified by in different lattice like BCC and HCP actually. But after removal of this thing, the lattice structure was getting, you can see the lattice structure, it was getting recovered back actually. Huh? So it shows the phase transformation is becoming maximum. It is becoming uh, reversible in when I'm talking about chemical based polishing process actually. So based on the MD simulation, whatever dynamics I have explained through MD simulation, so here you can see those dynamics I am now presenting in form of mathematical form actually. Huh? So here you can see the left side, there is abrasive, and abrasive is indenting on the workpiece. So what is happening? The chemical bonding, what I was showing, chemical bonding is taking place. So chemically reactive zone is taking place actually. And on the surface of workpiece, there will also a thin chemically reacted layer will also get formed actually. Huh? And when force will getting applied, so what will happen? This force will start rolling the workpiece. So on the right top side, you can see workpiece is rolling. Huh? So this is possible when we have ductile material. Why I am putting this ductile material? Because in case of ductile material, the applied force is very less. Fz is very less. Huh? So since Fz is very less, so it will not allow to move in translation actually. Here the bonding force will start dominating because external force is less. So bonding force will dominate, and bonding force is assisting for rolling only. Huh? So it will roll actually. So due to rolling action, the reacted layer is getting removed from the workpiece. So you can see how material removal is taking place. But in case of brittle material, if you see the right bottom side, what will happen? It will have more pressure or more force actually. So it will do both actually, rolling as well as rotation. And chip will start getting formed ahead of the abrasive particle. So you can see ahead of abrasive, chip is also getting formed. But in case of ductile, the chip was getting formed just beside of the just behind of the abrasive. But in case of brittle metal, chip is getting formed ahead of the abrasive particle. And you can see how forces is getting is coming on the abrasive particle, the axial force, then uh, lateral force, and the this rotational moment actually. Huh? So now here I'm just showing the glimpse. As here I showed in the bottom right side, brittle material chips is getting formed ahead of the workpiece. So that is shown in the MD simulation result as well. In the bottom result of silicon, you can see silicon is brittle material. So you can see the chip formation. It is getting formed just below abrasive particle and ahead of the abrasive particle. But in case of top aluminum uh, 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 polishing, you can see the chip is getting formed along with the rotation of the abrasive particle. So that is quite matching with our model actually. Now the chemical reaction I have conducted, and there what we found, the rate of chemical reaction. So you can see at the bottom left side, I have shown minimum reaction rate in case of potassium hydroxide, maximum in case of hydrogen peroxide, then in between nitric acid. Huh? So it is better to go ahead with potassium hydroxide because controlling a chemical reaction is very, very difficult. So it is better to handle a low chemical reaction. Otherwise, what will happen? Control on the process will not be in our hand.
So this is why potassium hydroxide is taken actually. Then chemical reaction is getting intensified with stress value. So you can see on the top or in any this thing, the chemical reaction is getting assisted by indentation force or the polishing pressure actually. So chemical reaction also helps to protect the work material, means the abrasive particle is not directly indenting the workpiece, so workpiece is getting protected. And the finished surface, you can see the top aluminum workpiece after removal of the material. The variation in the atomic layer is few atomic layer only, so it shows 0.5 nanometer deviations can be possible actually. Then based on this study, the entire CMRF process was mathematically modeled, and you can see right bottom side, I have proposed one mathematical equation. So this mathematical equation derivation, I'll not go in detail right now actually. So this equation I have used for further simulating entire CMRF process, because the MD simulation I can do for one abrasive and two abrasive, but that cannot be done for entire workpiece actually. Huh? As I told, MD simulation is applicable for nanometric scale, cannot be used for meter scale, because time and computation effort will be very high actually. For that, what we have done, this model was developed, and some parameter like tribochemical parameter like K chemical, viscosity, surface energy. So these chemical were computed by MD simulation, and that is used to solve this equation in FEA simulation. And this is the flow chart of the FEA simulation. So in FEA simulation, what I am doing now, I am computing magnetic field, magnetic force, then CFD to construct polishing pad and polishing pressure. Then CFD is again going to MD simulation to quantify finishing parameters like K, Km, gamma, surface energy, viscosity. Then mathematical modeling I am using, and finally FEA simulation based on the MDS quantified parameter and the mathematical model. Material removal computation is done through FEA simulation, and surface finish is computed, and the results was further explained actually. So here you can see the top left side shows initial surface profile that was computed from profilometer. So this profile you can see I'm showing in zoom view. So this is the y-axis scale is in nanometer scale actually. So this is it has got some initial few nanometer surface finish, not few nanometer, it is few tens of nanometer surface finish. Then it was uh, discretized by meshing actually. So right side, top right, you can see the mesh actually. Then that FEA simulation was applied using MDS parameter. So you can see the surface finish was achieved up to 8 nanometer when aluminum is polished up to 10 minutes with 10% of potassium hydroxide. Then another result shows surface finish 16 nanometer in case of silicon, where time was 10 minutes and potassium hydroxide of 10%. And their surface with the mesh, it's showing, it looks like this actually. So by that, FEA simulation was conducted to study about the prediction of the surface finish actually. Now experiments was conducted. So in experiment, we have varied the working gap from 0.5 mm to 1.5 millimeter. Potassium hydroxide concentration varied from 0% to 15% actually. Then finishing time, I have varied actually from 0, 5, 10, 15, 30, and 40 minutes. And there are some fixed parameter like size of iron particle, size of abrasive particle, chemicals, additives, then rotational speed, feed of a workpiece, MR fluid preparation. So those things I kept fixed actually. Then experimental data are put against the FEA simulation result actually. So you can see the line actually, continuous line is FEA simulated results, and dotted lines shows the point line like plus dot or star line. It indicates experimentally obtained value. So these are quite matching actually. and you can see at the last maybe at 15-minute time actually the surface finish was obtained. In case of the top one is aluminium point, the top one is silicon actually, where surface finish RA is obtained up to 0.2 nanometer, and bottom is aluminium, where surface finish of 2 nanometer was achieved actually. So here you can see that surface finish from these two trends, surface finish improvement comes very fast initially actually, from 0 second to 5 minutes actually, and afterwards the improvement is very small. So this this complete modeling and simulation, it indicates that we should not do over polishing actually. Over polishing means if we'll polish more than 5 minutes, then improvement in surface finish is hardly a few percent actually, but it will take additional effort, additional consumables actually. So by cost it will not be economically viable. So we have to find out what is the critical time. So that critical time can be used to polish actually. So here you can see the critical time is varied actually in case of brittle material and ductile material both actually, and with chemical concentration as well. Like if there is 0% potassium hydroxide, then their critical time is almost 12 minutes in case of silicon. And when potassium hydroxide is 5% or 10%, then critical time becomes 5 minutes in case of silicon. Similarly, in case of aluminium, you can see the lower without potassium hydroxide, critical times is coming early actually. So here trends is different. In case of ductile material, critical time is low if chemical or chemically active species is low actually, like potassium hydroxide is low. But in case of brittle material, a lower chemical giving larger critical time actually. So this helps which material we are processing. So accordingly, we can set critical time, and our productivity and cost can be optimized. Now, if we'll see the scope of MD simulation for other processes actually, so it can obviously applied for casting like micro casting, nano casting. For example, at the bottom left, you can see the PMMA polymer. It was casted on mold actually, nano cavity mold. So that was done by some researchers actually. So if you are working with some micro or nano casting, so that can be done. Or in case of conventional casting as well, the interface can be studied. Ki, interface between mold and molten material, how mechanism is taking place actually, or macro scale MDS like coarse grain modeling can also be done for casting actually. Then in case of machining like turning, electrical discharge machining. So here I have shown in turning the tool at the middle figure, tool is there, then workpiece is there. So this turning can be modeled. Then EDM, electrical discharge machining, the right side figure. So the tool workpiece in between there is dielectric fluid. So when we'll give a plasma formation, then how material removal and dielectric fluid disturbance will take place actually. So those things can be studied. Then electrochemical machining, layer beam machining. So in layer beam machining, you can apply the laser heat and you can see how ablation is taking place. Then focused ion beam machining, there you can apply the bombardment by heavy ions on the workpiece. So sputtering phenomena can be studied. Then in joining, welding, soldering, brazing can be studied. Then super finishing. Then in case of mechanical testing like nano indentation, so the left side is nano indentation, right side is tensile testing actually. So nano indentation can be done to quantify Young's modulus, hardness, and other parameters actually. Then tensile testing can be done to find out the Young's modulus and the behavior of material ruptures actually. So those things can be studied by mechanical testing actually. Then in case of thermal aspect, the thermal conductivity or heat transfer coefficient, those things can be quantified using MD simulation. So here what you can do, the left side and right side we can put different temperature, or we can put uh, left side higher temperature, right side we can put uh, we can put we will not put any constant, and we can see how temperature is rising actually. So by statistical averaging we can find out the heat transfer coefficient. Now if you'll see a scope of MDS actually, as I told, in other field I can apply MDS, but these are the present requirement for MDS actually. So if you'll see the interatomic potential development. So many atoms interatomic potential are developed actually, but not all are developed actually. So if you'll see in manufacturing, like machining of tungsten is one of the key factors. So tungsten oxygen interatomic potential is not at all developed actually. Means reactive interatomic potential needs to be developed. So that is not done. So if you develop interatomic potential between tungsten and oxygen through reactive MD simulation, so it will be helpful for future researchers actually. Then for polishing of silicon using cerium oxide, silicon to cerium potential interaction needs to be developed. Then stainless steel reactive force field needs to be developed, like reactive interatomic potential need to be developed to study the chemical reaction part on stainless steel actually. Then mechanical and thermal parameter can be computed for FES simulation, where experiment cannot be done at different circumstances actually, like if you want to compute the parameter at high temperature or some flammable material like steel, copper, zirconium, magnesium. So in those case, without conducting experiment, we can find out these parameter, these FA parameter using MD simulation. So these are the conclusions. Here MD simulation has capability to compute materials parameter for FE simulation. MDS is suitable to study science of manufacturing process at nanometric scale or atomic scale. Then MDS capability has been experimentally validated for CMRA process. It means whatever process you have, you can also experimentally validate by some way. You will not able to validate exactly same MD simulation, because dynamics I cannot get by any experimental way, but some findings can be taken out by experimental means actually. Like if we were doing some nano machining, then chip morphologies, chip shapes, and tool wear. So those things can be quantified by experimental means, and MDS data can be used to compare actually. Then MDS can be used for other manufacturing processes as well, what I explained earlier actually. So that's all. Thank you. For any questions, I'm here actually.
Participant can ask question if they're having question.
I think either whether some participants are there or not, I'm not listening any voice.
Total 65 participants are there, sir.
Okay. So no one is asking.
Click,
it means,
you can click over the D, sir. It will show.
pardon? I'm stopping. I'm stopping my slide.
Yes,
Slide
sir.
sharing.
Okay,
And what you're telling? What I need to do?
so just 1 minute, sir. A participant, if no one is having question. Okay, it is my honor to extend my heartfelt gratitude to Dr. Prabhat Ranjan sir for his exceptional online session. I think despite not feeling well, Dr. Ranjan sir is unwavering and dedication, professionalism shown through he delivered a session full of invaluable insights into our advanced manufacturing AI simulation FDP sessions. Sir, your willingness to share your expertise under such challenging circumstances is truly commendable and inspiration to us to all. And we appreciate your commitment and your collective learning and effort you put into this session to ensure that we'll receive comprehensive and engaging presentation. On the behalf of our my organizing committee and the participants, we all thank you, sir, for your perseverance
Thank you.
and for contributing so generously and so our knowledge base. And we wish you speedy recovery also, sir, so that we can
Okay,
see
thank
and
you.
look
Thank
forward
you
to
so
the
much.
more
Thank you.
new upcoming session in future, sir. Thank you, sir. Thank you so much,
Okay,
sir.
thank you, Dr. Javed. Thank you so much. Okay, thank you. Bye.
Now, I would like to introduce our next speaker, Dr. Hemant Kumar, sir. One second. Hemant, sir, I think only joined. Uh, we are privileged to have Dr. Hemant Kumar, sir, as a distinguished speaker for AICT ATAL portal online FDP on AI and simulation in additive manufacturing. Dr. Hemant Kumar holds a BTech degree in the metallurgy and material science and engineering from the National Institute of Foundry and Forge Technology, Ranchi, and he earned his PhD from the IIT Kharagpur. Currently, Dr. Kumar serves as a scientific officer G level at a metal joining and metal mechanics division of Metallurgy and Metal Group at IGCAR, Indira Gandhi Center for Atomic Research, Kalpakam, Chennai, Tamil Nadu, under the Department of Atomic Energy. Dr. Kumar has made a significant and to original contribution in the field of hard facing and welding science and technology with particular relevance to India's fast breeder reactors, that is called FBTR. And his work also extends to advanced welding, hard facing, thermal spray coating, and with a notable contribution to projects such as the ultra supercritical reactors initiatives and international thermonuclear reactor ITER, and with over the 80 research paper contribution published in international journals, conferences, proceeding, he has a vital role in advancing material science and has a mentored a numerous of MTech PG students during for their research work. Throughout his illustrious career, Dr. Kumar has received numerous prestigious awards, including INS Young Scientist Award, Young Engineers Award, IEI Young Engineers Award 2011, 2012, and Shri Vallipa Eminent Engineer Award 2024, and so many. He is also recipient of a Welding Science and Technology Award 2023 from the Indian Institute of Welding that has been honored with the multiple DAE Group Achievement Awards. Dr. Kumar is actively engaged in professional organization and holds memberships and fellowships in several prominent institutions, including Institutes of Engineers India, the Canadian Welding Society Board, Association of Indian Institute of Metals, Indian Institute of Welding, Indian Nuclear Society, Metal Research Society of India, the Tribology Society of India, the Indian Science Congress Association, the Indian Society for Non-Destructive Testing, and the Indian Laser Association. With an illustrious career dedicated to the material science and welding technology, Dr. Kumar incites a premises and to invaluable to all our participants. We eagerly look forward to his enlightening session. Uh, Sir, now you can start your presentation, sir.
So thank you, Dr. Jubair, and good afternoon to all of you. And thanks, Dr. Jubair, for nice introduction. And I am here to just share some of the work which we started doing on WAM, that wire arc additive manufacturing. And hopefully all of you have also gone through so many other module of these courses where you are familiar with these things. So am I audible, Dr. Jubair?
Yes, sir, you're audible, sir.
Okay.
Your voice and your
So,
video both are clear, sir.
okay, very good. So, thank you. So now I will just try to open and try to share that my slide. And
Please check it once, sir. MS, sir.
Hello. Hello.
Might be network issue.
I think there is a network issue.
Sir is trying to connect due to some technical issue. If the connection has been lost, sir will join within few minutes.
Yeah. Now it is all right, Dr. Juve?
Yes, sir.
Okay, so I will just share. I will just go to share and screen sharing. Okay. So I will go for entire screen sharing. Share. Yeah. So my screen is visible.
Yes, sir. It is visible, sir.
So okay. So sorry for some little bit disturbance. So I'm just going to talk on prediction of solidification structure of stainless steel deposit made using wire arc additive manufacturing route. And I am from Indira Gandhi Center for Atomic Research, Kalpakkam, as Dr. Jubair has already said in his introduction. So why I have chosen that? Because it was told to me that we have to discuss on industry 4.0, which is on latest where industries and manufacturing sector is progressing. So I have suitably I have just given him on topic on wire arc additive manufacturing, which I'm just going to talk on prediction of solidification structure of stainless steel during this process. So the my layout of the presentation will be, first I will be talking on introduction. So most of you know about additive manufacturing, and additive manufacturing is it is a general what is called term which we used, but it has lot of variants and uh, which I'm going to cover. It is a variant of direct energy deposition and with wire arc additive manufacturing, which in subsequent slide I will also show you the what is called the other additive manufacturing routes also. So and then application and advantages, and I will discuss here, since my talk will be mostly focusing on wire arc additive manufacturing. So I will be talking on cold metal transfer process, and I will be taking you to there to how to know do the thermal modeling of VAM, and based on that how you get the desired structure of the deposit. So for which that experimental and governing equation I will emphasize, and I will discuss a few of the results and discussions, and then I will conclude.
Sir, it is gone. It is again gone. Hmm? It is not audible. Due to some internet connectivity issues, the connection has been lost. Sir, we will back within few minutes. I just spoke with him. I request participant, please mute your mic.
Hello, Jubair.
Yes, yes, sir, you're audible, sir.
It is audible. You just see, I will show you the slide. Again, I
Sir,
will share.
you do one thing, sir. You switch off your video camera.
Acha, acha,
Sometimes
acha.
it takes more
Correct,
data.
correct, correct. True, 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 true. So I will just do just a minute. I will share you the slide. I will just close it. I will go to share screen share. Share entire screen. Share. So maybe video, because of video, maybe sometime it is happening.
Your screen is visible, sir, now.
Now it is visible.
Yes.
Yeah. Now it is moving.
Yes, sir, it's visible, sir. Move on, sir.
Okay. Okay. Fine. Fine. Okay. Thank you. I will be calling if some disturbance will be there. Okay. So sorry again. I don't know. Maybe because of video bandwidth, some issues. So what I was just about mentioning that, I was just telling that relationship between cost and geometrical complexity in AM versus traditional processes. If you very carefully, if you look this plot, what is given in this reference, which I have mentioned in the below, that when we look at manufacturing cost per unit versus the geometrical complexity, when you have a simple geometry of any parts, then traditional process cost advantage we are getting. But when we have a very complex design, as you can see as I am moving my cursor, if you look that when you have that blue line, when you have a complex AM design, then you have a what is called advantage over your traditional process compared to your additive manufacturing. So most of the time I have seen that people are started comparing with the AM or additive manufacturing part with the traditional process part. It is like it is no comparison unless you have a same geometrical complexity. Otherwise it is very difficult to have a better comparison and better understanding. So as I was mentioning that as ISO and ASTM standard has also described that the variants of additive manufacturing. If you look at that right side, we have a different variants of around 7 different types of variants, starting from the powder bed fusion, where we use laser and electron beam for melting this. Then we have a direct energy deposition, which I'm talking about today on wire additive manufacturing, which falls under direct energy deposition. We have a binder jetting, which we have sheet lamination, material extrusion, material jetting, and VAT photopolymerization. So these all falls under a broader classification of additive manufacturing. But today's my talk will be confined only on direct energy deposition and only on VAM. So if you look that alone direct energy deposition, this direct energy deposition we call as mostly DED. So it is defined as an additive manufacturing process in which focused thermal energy is used to fuse the material by melting as they are being deposited. So this DAD is an umbrella term. Hence, if wire, if we use as a feedstock material, and if you use arc, that our no as a energy source, what we use generally in our welding, then this DD is nothing but it's called as wire arc additive manufacturing, because we use wire and we use as arc as a additive manufacturing process for direct energy deposition. If you look again that direct energy deposition, we have either feedstock material either in the form of powder or either in the form of wire. So now, if you use powder, then as I was mentioning earlier, we can go in some other routes. But if you use wire as a feedstock material, then I can go for either electron beam welding, arc, or laser beam welding. So these are our energy source. So as I said that you take the energy source, you take that, it gives you a variant of other combinations. So when I take a wire as a feedstock material, when I take arc as a heat source or energy source, then we have a 3 variants starting from MIG or CMT. I will come later on when I will talk about CMT. We have a TIG, which is all of you are familiar at this stage, and we have plasma arc welding also. So these are the in process. So if you look this combination, it will give you a lot of combinations, but this today we are talking about wire, we are talking about arc, and we are talking about here first, that is CMT, so which I am going to be talking in this my presentation. So as I told you, major VAM components, so it is energy source, it is control motion mechanism, we require either CNC or either we robotics base, and feedstock material. If you look this typical schematic, what you required for VAM as a VAM setup, you required as a controlled motion mechanism, either it is, as I said, that it is either it is robo or CNC, and energy source, this we want either it is, so if you use wire arc additive manufacturing, then mostly welding power source. Otherwise, if you go for laser, then laser or electron beam source, and feedstock material here it is wire, in some cases it will be powder. So if you look the application of what is called additive manufacturing, so in past it is many components were have been reported in the literature which were made by the additive manufacturing process, mostly by wire arc additive manufacturing process. So these are some of the examples which is listed on the left side, where you can see one small pressure vessel which was made by a twin wire arc additive manufacturing process. You can also see one of the what is called the piping elbows, which also was made by additive manufacturing process for power industries. So what is the advantage when we try to consider wire arc additive manufacturing process with the your conventional techniques? I mean, not conventional, with the other DED techniques. The advantages of wire arc additive manufacturing is the high deposition rates. So you can just think of the deposition rate is of the order of something up to 10 kg per hour. So high deposition rate. Now this much deposition rate, it cannot be achieved in laser based DED. Deposition accuracy, okay, so it is not that great, but though it is less than 0.5 mm. And buy to fly ratio means what consumable we use and what is the efficiency of that, and layer resolutions, material usage efficiency, you can get close to 100%. And build size, it depends on your work envelope of the robo. If you just think of CNC with very large work envelope, you can build that much big component by using laser, which you can see on the left side, where two person is standing, and you can see the size of, and you can see the envelope of working envelope of the robo. So these all are the what is called advantages when we use wire arc additive manufacturing process. Now, as I said in the beginning, for our today presentation, I am considering on cold metal transfer process. So this process is a variant of what is called metal inert gas welding process. So why this we call as cold metal transfer? Because it is a relative terminology, and it is designed for giving a low heat input. So the low heat input of cold metal transfer process makes it an attractive option for energy source of WAM. In any additive manufacturing process, the heat input which it goes in the heat input which goes into the material system, we have to control it, we have to minimize it. So that's why this cold metal transfer process is very suitable for doing this additive manufacturing for wire arc additive manufacturing process. Now, as I mentioned just now, that CMT is nothing but it is a modified metal inert gas welding process, and it is also called sometimes metal active gas. And this CMT is patented by Fronius, Austria. And in conventional MIG and shielded metal arc welding and voltage and current respectively remain constant. But in CMT, both changes throughout the cycle, which I will show you when I will go to the right plot. Continual changes in current and voltage is caused by controlled backward and forward motion of electrode wire, which is a key feature of CMT welding. See, this forward motion and short circuiting mode of droplet transfer and backward motion helps in droplet detachment during short circuit time. By doing this, we can control the heat input in the CMT process. So the right side is, you can see very clearly, this here is short circuiting, and you see how it is happening, how the droplet formation and how it is happening. So if you look here, from here to here, this we call as arcing phase, and this is a short circuiting phase when it contacts, the droplet touches the base plate or substrate. So during this, if you just see that your current and voltage is not remains constant, it varies during arcing phase, which voltage should be very high, current also will high. But when it comes to short circuit phase, you can see there is a drop in the voltage. So we all know that the heat input total which goes, it is nothing but VI, and that's why we control the total heat input, or you can say that area under this curve in this CMT process. So this is a typical CMT standard cycle, and how it is designed that here wires also move front and back. Now, if you look at the measurement which is done in general, that your in additive manufacturing deposits or something. So what we do, we are more concerned concentrating on the what is the width of what we are going to deposit, what is the height and width height ratio and angle of contact. Not only that, I will just go later on, where we have also tried to correlate with secondary dendritic arm spacing and deposition rate, reinforcement area, dilution, and depth of penetration. So these are the some of the things which is required as an input parameter to optimize the model. So here maximum and minimum width by height ratio we have tried to correlate, and minimum to maximum dilution also. So you can see here how it is done. In the two case you can see that is spread, but height is not there, reinforcement height is not there, but in this case you can see. But when you merge these two, we should try to get in additive manufacturing like that. And additive manufacturing, as I said, it is layer by layer deposition. So it is called multi-layer deposition. So when you have a multi-layer deposition, we have to prepare multi-layer deposit and study the deposition quality and productivity trade-off, measure the build rate and dwell time each deposit. So if we try to do that, we can try to build the what is called the part, and we can also optimize, and we can also look into the microstructurally how this structures developed. So when we come to the thermal modeling, which I just now said, that basically we have to first see how heat we are giving and how we can model that the temperature or the cooling curve during the deposition. So this is a basic setup which you can see, and this is here you can see that a pyrometer is placed to measure the layer temperature at given point. Not only that, we use a CMT torch where we make a what is called deposition on some substrate of a 20 thick plate. And obviously when you can also have a thermocouple which you can place for measuring this temperature. So these parameters, if you look that in CMT, we have used 1.2 diameter 316L electrode. We have taken plate of same material, and as I said that we have used cold metal transfer. This is mounted on the CNC, and we have used pyrometer for temperature measurement, and we use various parameters which is based on our understanding, and we use pure argon as a shielding gas. And for all experiment, we keep the contact tip to workpiece distance always constant to 10 So if you look at all this modeling part, so it is a very common in all any arc process. Most of you have already used this. We used a double ellipsoid model proposed by Goldak in this heat source model, which is given in the equation 1. And then also we have considered the efficiency of this total heat input. So as that one of the advantage of this is that we have to go for length of double ellipsoid. That is, as I said, that it is a mix of two ellipsoid, and we have to take these all the parameters in our model. And based on this heat source parameter and other things, we have taken this, considered these all values based on our calculation and thermography image. We have taken these all parameters for our calculations. Now, if you look at the different sort of equation for heat transfer equation, so most of you are all mechanical background, and you know what are the heat transfer equation we use for conduction, and not only conduction, even convections and radiations. So these are the parameters where you can look that equation 2, that first equation, which is used for 3D heat transfer equation, where temperature we have T is nothing but is temperature, unknown temperature, and Cp we have taken for this heat capacity, mass density, rho we have considered, and K thermal conductivity which we have taken. Q is heat input, total heat input, which I shown in the previous slide, and total time also we have taken as a T. So these all that if you look at any what is called physical properties like your density or thermal conductivity or heat capacity, this all is a function of temperature. So we have considered that into this. And equation 3, if you see, this is equation 3 is nothing but it's equivalent heat transfer coefficient, which accounts for radiation as well as convective heat transfer. And for this emissivity, we have considered 0.95 for that. And if you look at equation 4, which is a conduction boundary condition which is applied between the deposit and the substrate, and also the radiation and convection which is applied to the surface of the deposit and substrate, which is given by this equation 4. So these all parameters where your epsilon is nothing but it is a Stephen-Boltzmann constant, and H conductivity is the convective heat transfer. So these all equations it is used, and these parameters, many parameters we have used with the function of temperature. Now, based on these two inputs, it is a very simple model. So no, on deposit was made, and you can see this cross section of and deposit length is constant. We kept around 100 length deposit, and we assume that there is no what is called transfer or heat taken away from the base. So we assume that this boundary condition, the base is insulated, there is no heat transfer, and these all we have considered. So if you see this, we have used COMSOL 5.4 for this developing this axial symmetrical model in XY and reduce the computational load. And non-uniform meshing was done, which is approximately 0.2 hexahedron mesh, which was applied to each source. And portion meshing we have used for substrate because that was not of great of interest, because we want to cut down the total computational time. And average layer thickness which we measured in this condition, it was approximately 1.6 and we have used 8 nodes in z direction, and total this much element we have used for these studies. To analyze the mass flow effect and domain activation, which we used some FEA type of finite element type of model, where we have divided each layer into 4 equal sizes domain, which is there in along the deposition direction. So this is a schematic which we have used, where we have initial temperature of the detector domain was equally set as the uppermost temperature of the underneath domain, which is the basically starting point. So with this, this is the cross section where z direction we are building this, and we just take the initial temperature of the activated layer. Like that, we go to as subsequent layers. So if you, by doing this, the what is our interest is that to look into the temperature profile at given time of that layer. So here, if you look, it is it is showing that at 3rd layer and 6th layer and 9th layer and 10th layer, which is the time scale is also given 45 seconds and this much time seconds and directions. So how this thermal model gives you the molten pool temperatures and the previous deposit, which is of the order of this. So this gives a understanding that what is the temperature of that region. So that what is the temperature distribution even when we go for layer by layer deposition. So that is very important. So for odd layer deposition, we have, as I said in beginning, we have started with zigzag fashion. So means first layer we are starting from one side, and as second layer we come to this side. Again we go like that. So it is in zigzag pattern, and what we got it is from this that that the molten pool temperature is almost like it is going to its melting point, which is approximately around 1400 degrees centigrade, and size of the melt pool, it basically increases as the number of layer increases. You can see here, this is the melt pool. So this is basically, it is one of the reason why in heat additive manufacturing you have a heat accumulation. This is the reason, because it is continuous phenomena and the heat is already built up. So with the time, with the number of layers, as you keep on going up and up, your heat pool size also increases. So this is one of the area how we can think of and how we can model it. So this after doing this, it was that same thing as I said, that thermocouple was placed on each passes. So if you look that this is the schematic of the cross section, where the 10 layer of deposits was made, and the thermocouple was placed on this point, because if it is placed at substrate, we will not able to get the correct figure, and we cannot place on the bead, on the first bead, because it will melt off. So we try to at least build some of the layer, and then try to punch the thermocouple, and then try to get the exact temperature, exact accurate temperature of the deposit. So this was done, and figure A and B is the basically we try to take from thermocouple the cooling curve, which is shown in the right side of the plot. And in one case we have given there is no dwell, it is 0 dwell. Another case we have given 60 seconds of dwell time. So in these two cases, if you look this curve, so during deposition of third layer, the 50% of second layer was remelted. That we have assumed that because this is overlapping. For good bonding in additive manufacturing, we have to remelt the previous layer. So that is our consideration. So that at least we assume that previous layer which we deposited, it is getting remelted, and there is a good bonding between that. So this is also one of the reason why we have gone with 50% of melting of the second layer. And the temperature of the mix phase in second and third layer was not accurately measured because thermocouple is so close that we don't get a correct reading. But apart from that, when we merge this thermocouple, then all readings has come perfectly all right. So this is the things which we have observed. So second and third layer error were more, but subsequently that error of these measurements was reduced because our measurement of accuracy was more. So if you look that in 0 degree, in 0 seconds cooling, so what happened that your cooling is that your experimental and what we get the from the heat what is called thermal modeling. So this is there is huge what is called in first 3 layers you can see there is a mismatch, but subsequently it has a better fit with the experimental and simulation things. Same thing is also observed in case of our 60-second dwell. Second and third and fourth is not matching, but as we go there is a good match between the experimental and simulation. This is happening. Why it is happening things? Because that second third layer, as I said, that the thermocouple is so close that we were not able to measure that. So as it goes up, we are able to, that accuracy of our measurements improves. So whatever we calculate from the experiment and whatever we calculate from the simulation of that previous things, it basically improves. So by using this, now we have a cooling curve. So now we try to take this temperature versus time of different passes. Now you can see that what is the peak temperature of second layer and what is the peak temperature of 10th layer. So based on that, we try to understand what is our predicted microstructure. So as I said that if you look here in the 0 degree 0 seconds dwell time and 60-second dwell time, totally overall this is our that the cooling rate of the different layers. So with the layer and with the cooling rate, it is the predicted cooling rate of your 0 seconds and 60 seconds. So if you just see here 60 seconds, because we hold it, so that cooling rate is much faster in case of 60 seconds, because that substrate temperatures comes down to it comes down to at lower temperature. So your cooling rate is much faster. So this also we try to see key effect of giving a dwell time in between two layers is also very important, which you can see here clear cut difference in the cooling rate of these two, that is without giving any dwell and with dwell of 60 seconds. So many times we see that many researchers and many people, they try to give dwell time between these two passes. Why? Because it has implication on the its microstructure evolution. So as if you look this figure A, it shows the cooling rate of each layer, and which I have just not told that it is evident from that overall cooling rate is higher for when we give 60 dwell time, 60 seconds dwell time compared to no dwell time. Now, if you take this cooling curve, now just if you know the cooling curve, what we can do, we can also determine the secondary arm spacing, which I mentioned in my beginning slides. So if you see the secondary dynamic arm spacing, which is we call as S dash, because this has impact on the mechanical property, not only the microstructure but also on the mechanical property. It was measured by the optical microstructure. So you take the optical microstructure, you measure the secondary dendritic arm spacing, and not only that, as well as simulated model, which we have used this lambda 2 equal to 50 GR minus 0.4. This is equation which is already reported in the literature. We also have used this, and where your this GR is nothing but it is a what is called cooling rate, which is in Kelvin per second. And secondary dendritic arm spacing we generally take into the micron. So considering these two, so what happened that we can calculate or compare the measured S dash, that is secondary dendritic arm spacing, with simulated secondary dendritic arm spacing. Means one we can take like a actual one we can take the microstructure of that layer. I will show in the second subsequent slide. We can take this microstructure of second layer and we can measure the S dash. And by using this cooling curve, by using this GR, that is cooling curve, we can also calculate the lambda 2. So these two approach you can also predict and calculate. So it is evident that both cases up to third layer S dash is almost similar, but cooling rate changes after fourth layer. So if you look here in this plot, so the first plot, if you look, the one is experimental and another is simulation. Another one is that without dwell time, another is with dwell time of 60 seconds. If you just see here, there is a there is a what is called not greater matching, but there is a good amount of matching. But if have cooling rate of 50 what is called Kelvin per second, there is a huge difference in this predicted value and as well as the measured what is called dendritic arm spacing. So this is one of the what is called the reason why we are not able to measure. So when we try to see this, we found that the cooling rate when it was low, about 14 Kelvin per second, the validated S dash have 30% error. But when simulation results, with the simulation results, however, in the higher cooling rate, above 40 Kelvin per second, the simulations results were more accurate. So this is one of the what is called results which we try to look and try to find out the dash without going for our actual measurement by optical microscope. Now this is another interesting things which we try to see from what is called layer by layer deposition, because each layer will have a different cooling rate and different chemistry of that. So this particular slide where we try to use the chemical information of that layer and try to see what sort of microstructure will try to evolve. So if you look this is a very typical cross section of the Safler diagram, where you can see the different mode of solidification with temperature. Now, if you go with Safler diagram, where you can have a chrome equivalent and nickel equivalent. So what here it is done, we have to calculate what is the chrome equivalent and nickel equivalent for wire, and what is the chrome equivalent and nickel equivalent for the substrate. And and also what is this chrome equivalent and nickel equivalent for the deposit. So if you see that deposit cross section, whatever you extract, you can extract so you can extract that sample from that deposit layer and you can do a chemical composition measurement. So you can just see here, this is a example where these two microstructure is given from the first and second layer of IPT60, where we have given 60-second dwell time. This is the SEM micrograph, and based on this SEM micrograph, we can determine the what is this chemical composition. So here you can see this chemical composition of first layer, chemical composition of the second layer. So this is done by using what is called SEM, scanning electron microscope, that is energy dispersive spectroscopy. So now, if you go to the Safler diagram has clearly given what is chrome equivalent and what is nickel equivalent. So based on this chrome equivalent and nickel equivalent, you know what is the composition of your substrate. You know what is the composition of your filler wire. So when you put these values, chromium, molybdenum, silicon, niobium, or even manganese for nickel equivalent, carbon, nickel, other things. So you get two values. One is chromium equivalent Another is nickel equivalent. So this chromium equivalent and nickel equivalent calculated for substrate and for filler wire is given here. So this is calculated value. I will not go much detail in this. I have given the equation. You have a chemistry, you can just calculate and put it. Now, same thing, but same equation is used for these two results which is obtained from the ADEX. So you take this value, you take this value, you try to substitute these values in this equation. Hello? Hello?
Yes, sir, audible, sir. Someone mic is on.
Yeah. Okay, no problem. So these values you can substitute in these equations. So after substitution, you will get this type of value. Now, based on this chromium equivalent and nickel equivalent, so what we can calculate the chrome equivalent by nickel equivalent. So this is one of the ratio. Now, here also you can calculate and see. So when you calculate for these values, for ever table values, what you get, you can see that the value varies from 1.48 to 1.95. Now, when we come to the isotherm of that solidification mode, if you look this pseudo diagram, ternary diagram, you can see here with the temperature and with this value of chrome equivalent by nickel equivalent ratio. If you look this red line, so here this red line is between 1.48 to 1.9 what we got. And if you look here, this window alone and this window alone, and when you see, this is basically nothing but it's a ferritic austatic mode. So it means whatever I am going to deposit, it will solidify in ferritic austatic mode. So that's the what we get it. But when you look in this mode itself, in ferritic austatic mode itself, you have a 1.48 to 1.95. It is varies that chrome equivalent, nickel equivalent. And when you go to lower down to that closer to 1.48 value, that our microstructure basically consists of austenitic and skeletal ferrite, which I will also show you in subsequent slide. When you have a higher one, that is 1.95, basically you will get a austenite and lithiferrite. So this is the common morphology of solidified stainless steel structure. And one thing is very clear based on the chrome equivalent and nickel equivalent, that your solidified macrostructure, you will get always in ferritic austatic mode. Means what does it means? Means your high temperature, whatever you are depositing, it will be in liquid. Now, as you lower down the temperature, it will solidify first to partially, it will solidification starts occurring and you get a delta ferrite. And subsequently, this liquid will remain liquid, and this delta ferrite try to slowly transform to liquid, delta ferrite to austenite. And at the end, this complete transformation occurs in the austenite to delta ferrite. So this we call, because here is a ferrite and here is austenite, we call as ferritic austatic mode of solidification. So this is only possible when you have a chrome equivalent and nickel equivalent, which is greater than 1.5, which is here. Now, in our case, we have observed this. Now, if you now we have already taken the cooling rate in earlier. I have shown you the curve of how we got the cooling rate. And now another thing which we get, that solidification map, how we can generate the solidification map based on the temperature gradient and the growth rate. So if you look this figure, it is clearly given a correlation between the temperature gradient, which is given by G, and growth rate, which is given by R. And this nothing but if you take this temperature gradient, that is G, and if you take that growth rate R, this multiplication is nothing but it's called cooling rate, which I have shown in the previous example where you have seen this in equation 4, that is GR, which is nothing but the cooling rate in Kelvin per second, and which you can get it from either from the your data which you collected during the experimental things. So based on this, if you have that information, you can have what is called two things. One is that at lower cooling rate where your GR is low, and another is your higher cooling rate where GR is high. Not only these two. Now you have a ratio also. You have G by R. So G by R is in one case it is higher, in one case also it is middle, or in one case G it is lower. So when you have a combination of these two, where which I have mentioned that G is nothing but temperature gradient, which is the rate of temperature change according to the distance of solid to liquid interface, and R is nothing but it's a growth rate, which is basically speed how your solid front is moving in the solidified microstructure. And this GR, which I have already mentioned that in solidification modes generally we take a combination of G by R or G into R curves, where G by R value affect the morphology and of the microstructure, and GR value affect the size of the microstructure, which is your cooling rate, governs by the cooling rate. That's why we call many times you also have seen, or you also have heard, higher the cooling rate you will get a very fine microstructure, lower the cooling rate you get a very coarse microstructure. This normal phenomena which we talk in our day-to-day activities. That's why that is the our what is called background of what we get a difference of annealing and normalizing. So in annealing our cooling rate is less, so we get a grain growth, but in normalizing we get a very fine microstructure because cooling rate is not that good. So that is for nucleation and grain growth. So all those things is also valid when you deal with any liquid transformation into the solid. So if you see here, when your G by R, G into R means multiplication of that, if it decreases, to a coarse microstructure form, whereas if G by R increases, your fine microstructure is obtained. So if you see here, this gives you, sorry, so this gives you what is different type of morphology involved. You can say that if it is lower everything, you get a coarser microstructure. If you get a very high, you get a fine microstructure. But within these two boundary, you have a different morphology. You have a planar morphology, you have a cellular, you have cellular dendritic, you have columnar dendritic, and you have equiax dendritic. So this morphology of this microstructure, it depends on G by R ratio. So higher the G by R ratio, you will get mostly planar. Means your temperature gradient is very, very high and growth rate is small. So in that case, you get G by R, G by R is very high. So these types of morphology which we evolve when you try to deposit. So now coming to that same what I told you and what we try to correlate and what we try to get it. So if you see here also we have put that growth rate of different layers. It is plotted for different layer. You can see that growth rate is plotted. Not only growth rate, if you look that here temperature gradient also we have plotted with the different layers. Now if you multiply these two, if you just imagine that I'm taking this value and I'm taking this, and with this layers itself, if we multiply this R and with G, we try to convert into the GR. That is basically it's a cooling rate, which I earlier I showed you that yes, this earlier I showed you that this is the things. So when you try to get that, when you try to get this for each layer, as I said that for each layer you have to calculate 1 to second first layer to 10th layer. If you calculate this, you get this type of curve. And if you see here in all the layer of the deposit, if you carefully see this, as the number of layer increases, you can see here what happened, our cooling rate is decreases. Not only that, it is also indicative that our temperature gradient and growth rate also decreases. Now this is temperature gradient reduction is very, very important because there is heat accumulation. So the cooling rate, definitely first layer will be much, much faster as you keep on building subsequent layer, because previous layer you have heated up. So that heat accumulation is there, and that is not allowing the subsequent layer to cool faster. So subsequently, as you keep on going, your cooling rate also keeps on coming. So this is one of the challenge in additive manufacturing, because this has impact on microstructure of different layer. So whatever your microstructure is there for first layer, the same microstructure will be not there for your second layer. So this is one of the what is called limit, or I can say one of the uh, uh, bottleneck of additive manufacturing, that inhomogeneity in the microstructure or inhomogeneity in the mechanical property, or you have non-uniform or non-homogeneous property of in all three directions, because your cooling rate is not uniform at different layers, at different locations, and at different elevations. So this is one of the reasons that we have to consider this, how to normalize it. So this gives a good idea how it is done. Now let us merge everything, and I'm just if you look this is shown at no dwell time, means there is a heat built up. So heat will keep on built up because there is no dwell time is given. Means we are continuously, it means we are continuously pumping the heat into the system. So what happens when you completely pump this heat into the system? What happens? This will be there in molten condition for longer duration. Once it is there in for long duration, what happens? There is a tendency that molten metal will try to sag in the downward because of the gravity. So what you can see here, it is a clear indication as you go from bottom to top, that molten metal will try to come down because of the gravity, because it is there in the molten conditions for longer duration. But when you give a dwell, you take into account that this layer has subsequently cooled. So when you try to deposit the subsequent layer, what happened? It cooling rate is becoming fast, so that liquid metal what you are depositing in the fourth layer will be no longer will be there present there for longer duration. So these are one of the what is called advantage of how to maintain the straightness, or how to avoid this sagging of the molten pool when we make a long vertical deposit. So this is one of the reason why people also try to start using dwell time, so that we can control the waviness in the deposit when we make by any additive manufacturing process. So this is the one thing. So you can see here that two typical what is called cross section of deposit, and you can see here this is the build direction which I have told you, first layer, second layer, third layer. You can see that what is called that interface between the subsequent two layers, and you can also see here, and you can also see here there is a sagging, but in this case there is no sagging. So what happened? So the average, if you look the uniformity in the deposition, when you use the dwell time, it gives a very uniform layer, not only uniform layer, surface roughness of the side from wall side, it will be also improved quite a lot. So now coming to the most important thing, if you try to see the microstructure, in previous things I have already mentioned that if you look that all 10 layers, that up from starting from 1 to 10, the cooling rate is not same. Why cooling rate is not same? Because if you look the temperature gradient, it is also different at different layer, and the growth rate is also different at different layer. So because of this, we are getting a variation in the cooling rate from layer to layer, and based on this variation, as I was telling, based on this variation, we can evolve a different type of microstructure when we try to look into this plot. So merging these two, if you merge these two, you can see that this is 10th layer. Okay, you can see that we have a lot of equiax grain. But when you go for 6th layer, where you can have a what is called remelted zone and other things, you can see there is a mix of two layer. And these things, when you try to go on looking at not this macro, means here it is like trying to see that at interface and at what is called remelted zones and all. But when you try to see the uh, optical microstructure, what we can see here, you can see that lot of microstructure evolutions occur starting from the first layer to the 9th layer. And not only that, when we try to give this cooling rate faster, because of this giving 60 seconds of dwell time, you can see that there is evolution of lithium ferrite, which I have already mentioned in the previous things. Though the chemistry is same, though we are trying to predict this from ferritic austenitic type of solidification, but having two different types of morphology of the delta ferrite. One is skeleton ferrite, another is lithiferrite. So these all can be seen in this micrograph, which is very clearly highlighted at different layer. So you can see this first layer where cooling rate is very high. We can get this type of microstructure, and as you keep on going from first layer to second layer to seventh and to ninth layer, how this what is called morphology is evolving. So you can see that at top layer completely it is going to the skeleton vermicular type of the ferrite. So if you see this here, the heat accumulation is more in case of when we don't give the dwell time, which is a very clear from this, which I have indicated some time back. And when you have first, fifth, and ninth layer, this it is very clear that the sulfide macrostructure is of ferritic austenitic mode, and the microstructure was observed to be the mixture of austenite and skeleton ferrite and lithiferrite, and sometime also columnar dendritic was observed. This columnar dendritic, if you just go back where I have already explained you that this here you can see that there is no such things is predicted. This is all like a pseudo phase diagram where we are not able to see, but based on that your cooling rate, we can also see that, as I was mentioning, when your growth rate is very high, we have a tendency to get some what is called columnar types of grain. So sometime we also observe that columnar grain. You can see at certain location there is a columnar grain, and on the 10th layer of the microstructure, we clearly saw that there is a clear equiaxed structure, which is also predicted by this curve, where we can see that when you have a very fast growth rate, then we can get a equiaxed type of structure. So this is how we try to do that small things. And now let us try to merge with what I said, that we have to measure this what is called that secondary dendritic arm spacing, that S dash. Finally, actually, we have to link with the cooling rate, which we have determined this, and we try to correlate with the S dash. So coming to that, if you look that same thing, which it is put here, which I was telling you that if you look here, that temperature gradient and growth rate, and try to let us superimpose on this the value which obtained from the optical microstructure a measurement, that SDS measurement. If you superimpose, sorry. If you superimpose these values over that, so what we can see here, this solidification map which we get by the VAM. So you can see this growth rate is put it in mm per second, and temperature gradient is put it in degree centigrade per mm, or you can say Kelvin per. So if you look this, hello. Hello.
या वयामध्ये ना तुम्हाला सांगतो, आमची इथे एक सर आहे कमलेश सोरटे, त्याने जॉब सोडला, तो फुल टाइम तो SVNIT ला गेला बरं का. तर त्याला लुकडार खासायचे 60-70 हजार रुपये पगार होता त्याला. सोडून अक्षरशः असायचे की काय गेला असं तसं, ठीक आहे.
Hello, you have any question?
4 वर्षात माले सरांच्या
Hello, participant, please.
Hello, you have any question?
दिन नाव सर, त्याचं काही विषय नाही. तुम्हाला मटेरियल्स आवडतं ना, याला जे म्हटलं श्रीवास्तव, याला दुसरीकडे देतो ट्रान्सफर. स्टायपेंड 37,000 रुपये फुल टाइम गेले तर पहिले 2 वर्ष.
Hello, participant, please.
43,000 आणि अवधी ना 20% नाही.
So you have any question? Hello.
No, sir. Actually, there was a it was unmute. That's why maybe sound was coming.
Okay, no question, na?
There was a mute was here actually. Someone was unmuted, so background sound was coming.
Okay, so let me know if you have any clarification in between. I can explain again.
Yes, sir. Yes, sir. Definitely.
Okay, fine. So what I was just trying to tell this, with these values which we got by experimental and by measuring this through the cooling curve through this thermocouples and other from other ways. So what we try to correlate that we try to see this the GYR, which is in that columnar dynamic which develops during this temperature range, and boundary of the equax is less than the 10 degree per second per mm square. So in this study, if you look here, if you just see here, what happened, we can get for that S dash measurement for different layers. So if you look here, the first layer, that S dash is something around 4.47 micron. But as you come to the fifth layer, it becoming 8.29, and as you come to what is called something on the ninth or almost like a 10th layer, it comes to the 9.4, that is which is secondary dynamic arm spacing. So this is calculated based on the experimental value, as well as that what we have calculated based on the which I told you that based on this equation, that equation number 4, which is from the cooling curve of this. So there was a match. So but if you just superimpose these two and try to see that from here to here how these values, the G and R value changes. So if you look here, it is clearly given that GYR value is very high. That is something like it cools very fast. That is 690 degree per second. So that cooling rate is very fast, and that is only possible when you have a first layer. When you deposit it, immediately all heat is taken away by the substrate. So you have a very high cooling rate. That is this. And then as I indicated, that higher the cooling rate, you have minimum the what is called secondary dendritic arm spacing. So it is this. But as you go from first layer to second layer, and then we go to the what is called that where our GYR is something like from 690 to almost like 1 by 10th, you can take that reduction in the cooling rate is of the order of 1 by 10th. When we go, then almost my S dash is coming down to the what is called 9.5 or so. So what this indicate? This indicate that this has a strong, the secondary dendritic arm has a strong correlation with the cooling rate, which is determined by the growth rate as well as the temperature gradient. So this is one of the typical things which we also try to correlate, and we try to get this value at the surface level. So at the surface of the molten pool, the G is lower and R is the higher compared to the inside of the molten pool, and hence the equiax dendrite is formed at the top layer, which I just now I said that at top layer, that is 10th layer, the microstructure is almost like equiaxed on above of this. So this is why it is on equiaxed what is called microstructure or morphology formed. This is due to the what is called the G by R value. So if you look here, the G by R value, is almost like on the top, it is almost like 2 degrees centigrade per second per mm square. So this gives the distribution of the equiax dendritic at that region. Same way, when we look into the equiaxed dendrite at the top of each layer, which is getting remelted as the next layer, because as I said in my initial things, that there is you have to keep some remelted zone to have a better bonding with the previous passes. So that also kept into consideration, and because of that, the columnar dynamic in the previous layer grows epitaxially to the next layer, resulting in the anisotropy of the deposit. So this anisotropy in this additive manufacturing, it is coming because of the evolution of the not only microstructure but its morphology also. So this also plays a very important role, how we design and how we keep the parameters in additive manufacturing. So, so I'm just now concluding this, that a comprehensive experimental and numerical study on the multi-layer deposition of SS316 was performed to investigate effect of heat accumulation during the deposition, and the salient conclusions which I have already indicated are below. A numerical model of WAM was developed. Domain activation method was also adapted to analyze the mass flow behavior. Simulated and measured temperatures show almost identical profile except the peak temperature with about 8% error, and that was also putting thermocouple in the first layer. The measured and the simulated secondary dynamic arm spacing of the deposits were compared to investigate the heat accumulation. As a result, the equation regarding the secondary dynamic arm spacing size and the cooling rate was found to be more accurate over cooling rate of 50 Kelvin per second. So this is one of the thing that how we can predict, because so it is clearly indicated that the cooling rate prevails in each layer is not same. So that is the one of the what is called I can say that disadvantage of additive manufacturing, because we cannot control that. Okay, so that is the one of the reason why there is a variation in the microstructure and why there is a variation in the morphology. This variation of chrome equivalent and nickel equivalent was found between 1.48 to 1.95, which suggests that the solidification in this is ferritic austenitic mode of solidification, and subsequent that solidification map, which was constructed based on the growth rate and the solidification rate, is growth rate and the temperature gradient of each layer of deposit, which was suggested to control and predict the microstructure. And from that it was very clear that G by R and G into R and G by R were ranged from 68 to 690 degrees centigrade per second, and this G by R is varied from 2 to 33 degrees centigrade second per mm square, so respectively. So these are the what is called some of the conclusions from this particular study. Now I will just also give you, because I have still some time, so I will just give you that how many times we go for building the layer by layer and making the parts. But prior to that, it is better to optimize, how we optimize a single pass, or I can say that single pass bead, because that has influence on that. Why I want to say this? Because if you look very carefully, people generally ask uh, how I decide what is this size of this first pass, because depending on the size of this first pass, whatever we decide, that governs to build on this. So because whatever we decide, over that only we have to build, and what we decide first, that is very critical, because if you try to not optimize this, then what happen, everything whatever you build over that will keep on getting multiplied, and ultimately you will not able to control the, I'm not talking about microstructure, I'm talking about control the shape and size of the deposit. So when we consider the shape and size of the deposit, the basic fundamental what we considered is your bead width and bead height, and what we calculate B by W or bead by height ratio and reinforcement and other things. So for that I will just give you one of the, because this was totally on microstructural related, so I don't want to give that. So I thought if time is there, I will also give you some few what is called inputs to how to optimize this. So if you just yeah, so if you look this, you can see here very clearly when you are making one pass, how you can see that it is not same. You can see somewhere you have a very less bead width, but somewhere you have a very large bead width. In some case you have a reinforcement. In some case you can see there is a no reinforcement. In some case you will see that there is a improper shape, it is not going straight. So all these things, when you try to use wire arc additive manufacturing, these all becomes very tricky. So what generally we used to do, we used to optimize by using CCD, that is Central Composite Design approach. So we take a lot of parameters, because as you know, in CMT or in arc welding, you have current, you have voltage, you have speed, not you have many other parameters, but you cannot play with all at a time. So you have to only play with some wire speed or speed or current, like that. You cannot vary many parameters. So here basically, if you look here, these all here it is the current is varied, okay, and your wire feed is varied, and your speed, that welding speed is varied. So based on that, you can see that how the different combinations of first pass, which is the basic building block of wire arc additive manufacturing, is formed. So if you look here, you have to calculate this bead width, bead height, and angle of contact. This is also very important, because angle of contact will give you an indication how good bonding or how good previous layer is bonded with the current layer is bonded with the previous layer. Because if you have a better angle of contacts or less angle of contacts, means there is a proper seating of previous layer into the current layer into the previous layer. So these are the some of the things where you we try to go with also with ANN model, artificial neural network process, where we try to take into this characteristic of bead width, bead height, and angle of contact. So these things have been taken. So this just I'm trying to tell you that let's take the first thing is what is your bead width. So if you look here, you can see that I hope you can clearly find that bead width is not same in all the 5 cut cross section. These samples were cut from this what I showed you here. So this, if you cut, you get a clear measurement that what is the bead width of this deposit. You can see here bead width of this deposit. Now this is done with using your prediction is with your ANN model and RSM plot. You can just see and how you get optimize this. Now this is another where you can have a bead height. So now you can see here bead height is also not same in all case. You can see here bead height is marginal, but here is very high. But bead width same thing, and bead height also it's varying. And here also you can see that we used ANN and we use RSM to just correlate with the different wire speed varying from 2 to 3 meter of per minute and at different current, because we can vary this current. And in all the cases we have to use the, please remember, in all the cases we have to use other parameters constant. Otherwise what will happen, if you change simultaneously 1 or 2 parameter, you will not know where you will get end up. So these are the things. The most important is also we have considered, because for additive manufacturing we have to understand what is this angle of contact, because this has a large extent influence on the layer deposition. It is not that simple we deposit one pass over substrate and that's all. So it is also that how bonding with the previous pass, and how it is giving you very smooth roughness over the wall surfaces. So these, for this we have also tried to do and vary this and try to optimize by using ANN as well as RSM approach. You can see this angle of contact. So if you look here, we don't want like this type of things. We always want where you have angle of contact should be in type, in certain cases we want to have in acute range. We don't want to go as large as possible. So these things, if you try to take that bead width by varying this bead width, bead height, and angle of contact, this which I have shown you for different what is called welding speed. So you can have this all this correlation. Now again, same thing for your different parameters. You can also have ANN and RSM plot, and you can generate this. So what is the advantage of this? if you look at a whole of it, overall comparison of what I showed you in the beginning slide and what the cross section, you can get like this all bead cross section. In all bead cross section, you get like this. Now, if you look here, now our ANN and experimental and RSM. So we also cut, we measured manually by optical. These all are optical image you can see. So now, as predicted by the ANN and as predicted by the RSM, and as our current what is called values, experimental values, we try to superimpose all values, and you can see that this the bead width or the bead height or the angle of contacts. So what is happening? It is matching. In case of ANN, it is matching within the what is called deviation of mean absolute percentage deviation of something to 2 to 4%. But when you go to RSM, it is on higher side. So it means ANN is the best tool to get the corrective relation with the your experimental values and with the predicted values. So not only that, after that we also did some trials and we tried to validate by feeding into that model, and you can see here how this trials value we tried to fit into this model. And what was the observation was that it fit well with the ANN model, which you can see clearly that the black one is for experimental value, red one is for ANN, and blue is for RSM. So these are random. So first we used those experiments for making this, for teaching that, and this we used for validating this. Now when you try to see that validation, now again you can see here that ANN as artificial neural network has given a very good correlation with the experimental value compared to RSM, which is in line with the previous things. So these things these things are very important when we try to take the basic building block of additive manufacturing before going into the building any parts, or trying to freeze that what are the parameters we should take in wire arc additive manufacturing and so on. So this table is showing that the optimized dimension is required for doing the additive manufacturing, and this results is showing that how optimized bead dimensions is matching or comparing with the predicted dimensions. And when we see this, you can see here, this is ANN value of bead width, bead height, and AOC, and this is the RSM value. And you can see that error of this magnitude, it is much lower for our ANN in compared to your RSM, though there is some higher deviation or higher error have observed in the bead height. Okay, so these things also helps in determining that what are the conditions we should adopt. Because why this I have shown that because ultimately you want to deposit a 10 layer or 20 layer, or you want to build a some parts without any error. So whatever dimensions you predict, it should be able to deposit. And not only that, subsequent that my previous things also suggested that we can also try to predict the microstructure, not only predict the microstructure but also predict the what is called that morphology of the what we get it. So as I have already given and as I have told you, that these are the things which we used for optimizing and for determining the parameters, what I should select the bead width, what I should select to bead height, and what I should select for angle of contacts. So this basically leads. So this I have already showed you. So this you can see here somewhere you get some shape which is not desirable. So those things we have to omit, or which though we have to use that for training, but we cannot consider those parameters for our actual deposition during one. So now I think last I think 5 minutes I should have some interaction with you, because I don't want to keep on talking, and ultimately I don't know, because ultimately you have to get benefited with some of the what is called some of the idea or some of the concept which I have given during this. You can also because that it is time is very short. I can't give you more in detail like a classroom thing. So I just given you the purpose for this. My talk is to just give a outcome of the studies and how you can predict the microstructure, predict the morphology in a simple material which is treated as a like a full austenitic stainless steel, that is 316. So because it is easy to take a very simple system, so starting with simple system is much easier taking rather taking a very complex system. So because you will have a lot of other interference will also come into the things. So with I think with this I just close what is called my talk on this. And so thank you very much, and thanks Dr. Jubair for giving me opportunity to. But only that one of the disadvantage of online talk is that I can't see the faces of participant. I can't read them. I can't understand them. So here simple is only I am speaking. So with this, I just thank you. Thanks to all. Thanks. Thank you, Dr. Jubair.
Thank you, sir. I'm Dr. Manish.
Yeah.
Sir, I
Yes, sir, you
request
can
to
ask.
slide with all of us, sir.
Yeah. Manish. Dr. Manish.
I request to please share the slide with all of us because it is new to us to
Okay.
study at such a low level,
Yeah.
nanoscale level.
Okay, so what I will do, maybe next week, Monday, I will be not right now. I am not in station, so I am outside. So this is some of the works is done by my students. So I will just few things which is more of this. I will just try to remove and basic things. I will just try to send to Dr. Jubair. He will share with all of you.
Okay, sir. Sir, I also request to share the contact details with us. So in future, if you want to contact you, we can contact.
No, I
Yes,
did
sir, I will
not
share
get
you, sir.
Dr.
I will
Manish.
share, sir.
Dr. Manish, I am not able to get what you are asking.
No, I'm asking you to please share the contact details also, sir, to us. So if you want to get in touch, so we can get.
Fine. So you can, for any details, you can be in touch with Dr. Jubair. He is your nodal person. So all my details are with him. You can get from him, or you can also contact him for detailed PPT or any reading material or anything. So definitely we will try to whatever possible. I will try to share with all of you.
Okay, thank you, sir.
Thank you.
Thank you, sir.
So, Dr. Jubair,
Yes, sir. What anyone is
you
having
just
a question, please ask the question.
ask any participant if they have any doubt or any question, please ask. I think I have still 5 minutes. I think more or
No, sir, only
something like
2 minutes,
that.
sir. Only 1 or 2
Okay,
minutes. If
sorry,
anyone is having
2 minutes.
question, please ask. Sir, if no one is asking, I have one basic question. You done simulation, am I right, sir? It's a
Yeah.
double ellipsoidal gold-like model equations.
Yes.
Sir, when we are doing this multi-layer process, deposition process, now when we are
Yeah.
doing this deposition process, the back propagation, that heat, the last placed molten pool over the
Yeah.
molten pool, that may reheat the process, correct? As per our
Yeah,
multi-welding
that's why
process.
I use that. That basically what happened here, there is a superimposition because it is layer
Yes,
by
yes.
layer. So that is the one of the challenge what we have also faced. So for that you have to. That's why I said that in few cases you got that there is a experimental and predicted values were not matching. So what happened for that? What we did, we have kept our origin in the that we have taken on single point. So that is middle of the layer. If you look that 100 was the length, we have kept exactly at the 50. So it means and we have punched the thermocouple at the second layer. So means whenever that will go, that will only we will measure that temperature alone with that. And that golden model whatever we have, this is experimental which we have acquired from the thermocouple. Now that this value which we have taken that model, that no that golden, that double elliptical model, so there we have only used this heat what is we are pumping. We are not considering the previous heat which is already there on the source. So that was the we got some what is called mismatch also, because maybe this is because of this interruption of the previous layer which is having some heat.
Sir, which software you use, sir?
That I told COMSOL.
In the console. Okay, that but
Yeah, yeah.
that required, I think, some coding, no, for all this
Yeah, yeah,
information.
yeah, yeah, yeah. Actually,
Okay.
that done by my other partners, colleagues. So we try to do this. I think if you there is a one professor in BITS Hyderabad. He is also using COMSOL. So I think you are all are from Andhra Pradesh. Maybe you can have. They have one smaller or older version of COMSOL, and
Yes, yes,
you
sir.
can
In
have that.
SysWell also it
Yeah.
is available, no, sir. In our
Pardon?
Agicard we are having that.
Yeah, yeah. We
In
also
SysWell it is
have.
there, no?
We also have. We also have. We also have console at our place. And I'm just telling you because your institute is close to Hyderabad.
Yes, yes,
So,
sir.
so you are based from Telangana and Andhra. So I was just suggesting you that near an academic will be always better to academic.
Yes, yes,
So,
sir. Yes.
so that's the reason why I mentioned that. So
Oh,
I think then I
yes,
can.
sir. Yes, sir. Thank you, sir. Thank you so much for your time, sir. It's really, really honor to, and it's really privilege to listen your expert lecture, particular this field. Uh, 1 second, sir. Your willingness and your expertise in this particular area is really inspiring for us, and it's really appreciate to commitment this. And you still you're outside and you have given the presentation. Thank you, sir. Thank you so much, sir.
Thank you, Dr. Jubed.
Now I invite our next speaker. It is a pleasure to invite Dr. Sabyasachi Nilekunda Sabyasachi, a distinction expert in advanced materials and welding technology. Dr. Sabyasachi completed his PhD in Advanced Materials Engineering from Dongyu University, Busan, Republic of Korea, where his research focused on the evolution of the microstructure and mechanical properties in weld metal and simulated heat affected zone for structural application. He holds a master degree in material science engineering from National NIT Karnataka, Surathkal, and bachelor degree from Government Rajiv Gandhi Institute of Technology, Kottayam. Dr. Sabyasachi brings a wealth experience from over 10 years in spanning industry, academia, and research. Currently serving as a principal researcher at the Energy System Materials Laboratory at Dongyu University, Korea. His research encompasses extensive research on advanced high-strength steel, resistance spot welding, and high-strength low-alloy welding, with a particular focus on the heat effectors on metallurgies. His industrial background is equally impressive, having held a pivotal roles from engineers to general manager in leading organizations such as Alpha Engineering, Indira Gandhi Center for Atomic Research, and Superior Welding Technology Private Limited. This blends of academic rigor and practical experience uniquely position him to bridge the gap between the research and the industrial application. In addition to this professional and academic background contribution, Dr. Sabyasachi has received several prestigious awards, including IIW Best Indian Institute of Welding Best Paper Award category Metals and Metallurgy 2024, and multiple recognition from Korean Welding and General Society. His prolific output, including numerous publications in renowned industrial international journals and conference proceedings, as well as patents that underscore his innovative approach to welding and metal processing. Please join me with Dr. welcoming Dr. Sabyasachi, a dedicated researcher, visionary leader, and innovator whose work continues to push the boundaries of welding science and advanced manufacturing technology. I welcome Dr. Sabyasachi.
Uh, Thank you, Professor Zubair, for your kind words. Without wasting time, I will share my screen. So first of all, I would like to introduce my laboratory. So I'm working at Energy Systems Material Laboratory in South Korea. So precisely speaking, I can say that I'm now residing at Busan. Exactly from this place I am speaking now. So moving on, I will just introduce our laboratory at a glance. So Energy Systems Materials Laboratory is led by Professor Yongdo Park, a well-known name in the welding fraternity. So I'm working under him as a principal researcher. We have a number of projects, namely from both industry as well as the government projects. And at a glance, we can say that we are well equipped with all the welding machineries, basically the analyzing characterization devices, the simulation softwares, etc. And I will introduce to the basic current researchers. So we can see that we are funded by the government. We are working in very high strength steels, like the hot press forming steels up to 2.2 gigapascals used for the automotive industry. And we are also having different welding techniques, including the self-piercing riveting techniques, the resistance spot welding techniques, and so many other kind of sophisticated welding techniques. And we're also these are the some of the projects we are doing, and we also are collaborated company named Test1, which also is part of us. And our lab basically is divided into three parts, A, B, C, where the team A is joining mechanical fastening one, and team B is the welding for battery assembly and laser welding, which is quite interesting. We are majorly dealing with ultrasonic welding and laser welding for battery cell. Currently, we are undergoing the projects from Samsung STI, LG Energy Solutions, and also Lingus Japan. And we are also having very high, ultra high strength steel weldings, which we are undertaking the liquid metal embrittlement projects, the electro degradation things, and also some laser welding of the ultra high strength steels. So moving on, our laboratory is equipped with sophisticated welding equipments and all the non-destructive testing equipments. And we are also collaborating for other things. This is a new one, which is the battery welding machine, which is there in our laboratory. And we are also using some complex vibration ultrasonic welding in our lab. And yeah, this is the self-piercing riveted equipment made of bulloff, which we are using in our laboratory. And further, we are equipped with the Sorpus simulation softwares as well as the SimFact simulation as FIA softwares for the finite element analysis. And we also has the monitoring and welding techniques. And further, we have equipped with some 3D printers and all those kind of things. And now I didn't show here. We are also equipped with modern 3D scanning devices. So, not further wasting time, I would like to move to our today's major job. So, apologistically, I can say one part I am done very well, and the other part I can just take for you. So, let's go. So, our today's topic is the analysis of self-piercing riveted joints for lightweight vehicles. So, the first part of my presentation will be on the development of laser vision based scanning system for selection and optimization of quality attributes for the self-piercing riveting in modern car factory. So one of the basic things which we have to understand is that our car factories all over the world is already doing 3D scanning for the other quality inspections, but not the welding inspections. The welding inspection is comparatively new. The welding inspections, non-destructive techniques, we can say that majorly used include the ultrasonic testings or similar testing technologies. However, nowadays we can see some kind of CMT techniques are also equipped, which all are kind of time consuming. So with this, when we move on, basically an automotive car body is normally welded with resistance spot welding and gas metal arc welding in some of the things, laser welding, and also we can say that we are using the self-piercing riveting technologies. So why laser SPR is used? I couldn't put more things. However, I have shown some car body, which we majorly called as a body in white. So the body in white is introduced in order to reduce the weight and thus improve the efficiency, as well as we can improvise the carbon emission so that we can have a total improvement. So to reduce weight, normally we can adopt the aluminum or magnesium alloys or some kind of reinforced plastics and all those kind of things. However, the problem is when we use fusion welding techniques like resistance spot welding or gas metal arc welding or even the laser welding, as we know, there are metallurgical issues. Say, for example, for to join aluminum to steel, we know that the thermal coefficient of thermal expansion and as well as the melting temperature of the aluminum to steel is different. Aluminum is melted at some 670 degrees Celsius, whereas the steel, any steel should go up to 1500 and above. And also there is no common phases which forms with when the aluminum is molten with the steel. What happens is that we majorly get the intermetallics, namely Fe2Al5 are what we have seen from our experience. So as you know, the controlling of the IMC layer thickness as well as the hardness, the toughness of the IMC is very tough. So what we can do is without any melting, we can join these things and also we can get the required strength. So for this, a beautiful technique is introduced, which is very fast and no time consumption, as well as with very little defects and repeatability. We introduced the self-piercing riveting techniques. So currently, uh, our motivation is, we know that like I have given enough introduction. So due to the fourth industrial revolution, we are in the process of becoming a smart factory by applying technologies such as big data, AI, and IoT to the manufacturing industry. So as for weight reduction in the modern cars, like I already explained, the body in white which I have shown, and the SPR has a large role in the material joining. So the for destructive analysis in the automotive body quality, what happens is that nowadays we are doing, we can say that, say for example, a 40 bodies made, we test, and next 40 we test, like that it will go on, say for example. But what can be done, we can introduce a new technique, and which subsequently produces, we can apply as a non-destructive testing. So now what happens is that the destructive techniques requires the quality time, material, and a lot of human efforts. And if we go for some simulation techniques like the SORPUS, or for example, we go for the some of the other FE techniques, the results are more idealized and does not give the real picture about the quality of the uh, weldment, because this is we can't get the field variable. What happens? So many tiltings and gaps and so on and so forth. So many field variables will be there in the real-time welding, which cannot be seen with the simulation techniques. Subsequently, we have to develop a realistic, non-destructive technique, which can produce, which is needed for a modern small factory. So this could be equipped in the modern smart factory as well. So let me say this. Let me say that the objective of this work is to introduce a hardware-assisted surface analyzing uh, methodology, which can be fast and gives the real-time picture of the quality of SPR joining in a car factory. So let's introduce the state of the art. So nowadays, these are the destructive analysis. What we do is we will do the sample cross section, and then we check the, like you can see, the distance, the teeth I used to say, and head flushness. If it's too high, there is an issue. If it is too low, then there is an issue, and there will be possibility of the bottom gap. There is a possibility of top sheet gap, and all those kind of things. This we called, there will be a gap which, if no gap, we can say that the weld integrity will be higher. So these are the normal quality indications of a SPR joining. So this is the normal simulative sampling which I have shown over here. So the thing is that an automation is required in the simulative sampling, and also we can say that this is not a in-house kind of method. This is kind of a predictive kind of methodology, and which cannot give a real picture of what is happening. So let me say now the research objective of our current work is the non-destructive analysis techniques, which can be a solution to these kind of challenges which I have mentioned. So a real-time picture of the quality of SPR joining in the car factory is the need of the hour. So moving on, the technology development principle, let me introduce. So as I'm not sure, the modern car welding requires 1, 2, 3, or 4 kind of join material thickness combinations and different grade combinations for welding. So what is required is the optimum flaring of the SPR rivets. Thus, we will get enough interlocking. So we need to have a calculation of the plastic deformation so that we can predict the optimized die and the rivet combination for the particular material which we are joining. Thus, an SPR is applied with optimized rivets and dies so that we will get a good joining. However, like I said, there is no guarantee that this joining is always a good joining due to the field variables I have mentioned. So what is our major objective is to introduce a laser vision or laser scanning methodology to identify the top morphology as well as the bottom morphology of the joint, such that we can make a numerical or other kind of predictive equations to get the quality. So in short, in summarized form, I can say that we can in the factory we should have a 2-sheet or multiple sheet which we can give as the input variable and the material thickness combination as an input variable, such that will predict the rivet and die combination which can produce the optimized rivets, and the scanned results should immediately predict the quality of the joining. So further moving, what we have, the technology development principle which is the deformation of the SPR joining. We are kind of giving so many attributes as the SPR quality from the cross section, as I have shown here. For example, the head flushness in both directions, and this D1 is the material, how much material is drawn into the bottom die, and the diameter restriction, and so much and so forth. And then I have shown as of here, this top and bottom scanned ones will be cross sectioned to identify this thing, such that here also we will give named so many attributes, and we can say a rapid online monitoring system is developed. Now we have the 3D scanned quality attributes as well as the cross-sectional attributes. So what we do is now a triangular correlation of this has to be made. So like I previously said, the destructive testing of the SPR is done by the cross-sectioning of the SPR ends. If you can see in the resistance spot welding, what we do is we can just peel the sheet and check the nugget diameter and identify a quality attribute like 4 root is the minimum requirement or something like that. But since SPR is a mechanical joining, we cannot kind of peel the thing and do the quality analysis. So now the SPR has to be cross-sectioned, which is obviously a destructive technique, and an online data which can be obtained as the downforce versus displacement. As you can see, this is the downforce versus the rivet displacement curve, which you can use as a quality indicator. So although the cross-sectioning is laborious and time-consuming, it gives the original attribute with respect to the SPR joining. So obtaining the process curve can be real time and can obtain the quality data on the joining quality. So by using the laser vision or the laser scanning technique, it is possible to have a real-time online monitoring technique, which can be a non-destructive techniques. So there should be, since it is there should be a correlation between the cross section and the process curve and the laser vision or the laser scanning attributes. So subsequently, this triangular correlation, which with the cross section, process curve, and the laser thing, we can combine to characterize, to predict the SPR attributes. So we have developed a real-time quality monitoring system by combining these things, and which can be used online, which can be used as an online monitoring technology to characterize the quality of the SPR joining and predicting the quality attributes. So I'll show the how the things has been done. So this is the laser vision scanning technique, which is to which we can say two-dimensional technique. So we can just scan on the top, get the two-dimensional attributes. If you scan like this, we can get this kind of two-dimensional attributes using this laser vision scanning machine. And other is a high resolution 3D microscope, or commonly said as a confocal 3D microscope, which will produce something like this, which we can take out and get the cross-sectional attribute. Or you can use a 3D scanner, which will give something like this. So the validation of the quality monitoring system, RQM, is to be carried out by one-on-one correlations, and the cross-sectional attributes to the RQM attributes should be plotted and find to have kind of, we have to find the correlation. So yeah, this gives the how the 3D scanner as combined with the Polyworks software, and we can get the cross sections. So yeah, so this is the one which with the material thickness combination plus grade combination. This is the schematic of the rivet cross section. This is the schematic of the basic flat die combination. I have only shown the flat die combination. We have so many kind of dies like pip die, round die, and all those kind of things. For the easy understanding, I have only given the one kind of die. So what we did, we have developed a numerical solution to understand the basic attributes, quality attributes in the SPR, and the RL, as you can see, all we have developed some equations to find these things. And also the cross-sectional attributes, we have numerically identified some correlations. And finally, our aim is to correlate with the predicted equation and all the field variables. So the selection of the SPR, in summarizing this slide, the selection of the SPR die and rivet is from the database and from the simulation. And getting the database kind of laborious because we have to do so much things. So simulation data, like I said, it gives the ideal picture. So what we do, the mathematical modeling using the bottom material deformation calculations using the numerical techniques, and an algorithm is developed to predict the die to rivet combinations required, and the characteristic like the type of die and the rivet and everything can be given in the software to give the predictions. So the now it's time to validate the results. So yep. So the SPR validation has to be done. So we have given the boundary conditions like the cast aluminum to the 6061 wrought aluminum combinations, and the mechanical joining of the cast aluminum, as you know, it's a challenge as the deformation of the sheet may lead to the bottom cracks due to the poor plasticity of the material. So what we did, we applied the SPR algorithm to the joining and optimized the die as well as the rivet such that there won't be any cracks obtained in the normally we will get a lot of cracks. I should have put the cracked versions as well. I forgot to give. Normally when we do, there is a large possibility of cracks all over here due to the the cast aluminum, poor plasticity of the cast aluminum. So the application of the SPR algorithm, we can say as kind of optimized the joining conditions for the SPR. So this is another kind of situation, like a 3-sheet combination, the 60611T, 6061 to the 3T. One of the interesting thing is these all are the original automotive combinations, which is suggested by the Hyundai. So we can just say that this SPR algorithm can be used for the selection of die and the rivet for optimizing the joining. So the algorithm we can say for the scanning for the SPR joining, we can say that in production line, the die and rivet selection can be carried out from the database and the joining of the SPR and the quality attributes obtained through analyzing the cross section. So what we did is that an algorithm for the SPR has been introduced so that which can solve the die selection, rivet selection issues then from the basic knowledge of the material grade and the material thickness. From this, the joining is carried out with an online monitoring and subsequently a non-destructive analysis using the laser vision bar laser scanning system has been done. And this has to be further validated by cross sections. But we can, what we can do, we can, instead of some 40, we can make it 100 or 200 joinings, and then we can do the cross section. That is the benefit of this quality management system. So further moving, we can say that what we are now doing is the correlations between the cross sectional attributes, the process curve, as you can see over here, and the cross section has to be obtained. So we are kind of developed a qualitative correlations like the head flushness to the process curve things. The DT means this thing, DT to the process curve attributes, and the cavity gap to the process, something like that. So similar to this, we have also kind of now I will just introduce the how the laser vision scanning can be used to measure. So first we like I have said a lot of times, we will obtain the joining like this, and we can keep our samples like this. This is a very basic equipment which I have shown. So we can scan this to obtain the scanned result like this. One of the benefit of this is that the laser vision technique is a very faster technique. So now it's time to combine the cross-sectional attributes with the laser vision technique, which I am not wasting much time actually. So what we can do is the LVS and the cross-sectional attributes can be compared to obtain the relations between the SPR attributes, and further we can correlate with the basic quality attributes from the original measurements. So Further moving. Now, what we have done, we have to do the one-to-one correlation of the cross-section versus the laser vision data. So these things are head flushness, H1, H2, D1, D2, D3, all are the cross-sectional 3D cross-sectional attributes, I can say. So what we did is that the H1 from the 3D scanning and the H1 from the cross-section are validator, for example, to get a one-on-one correlation. So as you can see that this gives a good cross-sectional correlations. So the slight variation, so like in the towards the cross-sectional features, if it is there, is corresponding to the machining problems, we can say. So the identification of exact deformed spots for finding the deformation attribute from the bottom sheet can be microscopically done. And if there is a head flushness calculation deviation, we can say this part. So we can say this can be due to the surface correction issues during the scanning, and maybe we can say when we put it into the poly software, that can be an issue, we can say. So these are kind of negligible, and we can say that this has a very good correlations. So so this I have just shown here. As you can see that we used a flat die. So I'm just showing what the pip die kind of thing, and what all are the attributes we just has put here. And further moving, we compared the process curve to the 3D scanning, and also now this triangle is completed. We compared the cross section to the laser vision and get some correlation, laser vision to the process curve, and further the process curve with the cross section, all circle completed. Now the rivet quality monitoring, the RQM, we have to introduce to get the equations, numerical equations are developed to understand the attributes. So these are the equations which is developed. So what we have obtained is that you can see that the variation is very limited when we have tried a triangular correlation to predict the attributes. So thus this is the complete the deformed rivet diameter to the effective length variation, which you can see over here. So the effective rivet variation is only 10%, and it actually is further improved now with a lot of data which I haven't shown. So to summarize this part, we can say that the how the smart factory how the factory looks now, and how we can use it in the smart factory, the SPR quality management system. So we can say that this is the SPR joining, and we have the monitoring data, and this is the cross-sectional data, which are the normal quality measurement techniques. So what we do is we develop a database, and we put it in the rivet bar die selection algorithm and validate. And we can see that quality SPR quality prediction system, which can be imparted in this lane, in this assembly lane. And there will be a SPR joining, and simultaneously the monitoring data can be taken, and the material moved from the laser vision, moved, can be in the process in the factory. During the movement, we can take the laser vision and scanning things, and we can apply in the quality monitoring system, and in between we can do the cross section and get the quality attributes. So this is a software to do the die and rivet selection, and we can have a laser vision like a hardware assisted surface profiling methodology as shown here. Joining and the scanning can be done and proceeded with the joining part to obtain the surface qualities. And that's the things which is from the analysis of SPR processing, I mean the development of laser vision scanning system. So Professor Subair, should I proceed with some other things as well, or is it okay to stop here? Hello? 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 Am I audible?
One second.
Oh,
Yes, yes, you're audible, sir.
Yes, sir, you're audible.
okay. Thank you. I think I can quickly show some of the things. I hope I have some time, right?
You have sufficient time, sir. Your session will be
Okay.
5 to 6:30.
Okay, okay. I'll make it a little faster. So see here, these are some of the practical things which we have done in during our projects with the companies. So this one I have to show now. Let me be a little more casual. So these are the scanned things which we have done with the our modern 3D scanner, not the laser vision scanner. Okay, this is a 3D scanner which Creeform, I think, hexagon or Creeform machine. We have two machines. So this is the surface of the die we can see, which you can observe here. So this is one of the things. So as you know, the modern car factories, one of the important thing is to weld in the short flange. So welding in the short flange is a challenge actually. Normally we will do it with the resistance spot welding. However, what happens is if the top sheet is a steel and down there is an aluminum, or say for example the top sheet is a wrought aluminum and bottom sheet is a uh, cast aluminum, then the issue starts. The welding may not be that of high quality and may have some pattern issues and all those kind of things. So in this project, what we are trying is to develop a predictive system to find the minimum edge distance which can be kept to do in the original car factory. So I just try to define so much things, how the edge distance can be calculated and all over here. And we have given by varying the edge distance with respect to the die position, how this will behave. So there are three possibilities I have put where the absolute edge distance can be positive. That means it is here, practically speaking, and it can be straight here, leaving the cavity in the die here, and this can be at this edge. So as you know, with this picture, it is not that much clear. However, the flanges will be something like this. So welding in this area is good if there is no quality issues. So our intention is to get some good welding by keeping the edge distance minimum so that we can reduce the size of the flange, which in turn can reduce the vehicle weight and improve the efficiency as well as the carbon emissions in the petroleum vehicles. So, so normally this I have seen how this should have been shown in the last one as well, but this is associated with this project. So this is the monitoring data which we will get from the normal SPR machine. So I have divided this into 3 phases actually. To material, this curve will change actually from my experience. So we have divided into 3 zones: the positioning, the piercing, and the interlock joint compaction. From literature, actually, I have seen people have divided into 4 or 5 or so much things. So here, what we have done, I have just depicted is the Simufact software, the FA simulation software, how it shows the SPR stress intensities in which areas it is coming, how the bottom looks, how the edge distance looks, and all those kind of things. So in this project, actually, this I have put the table because to show which are normally used aluminum sheets in the car factory. So in the beginnings, I have shown the steel to aluminum combination, and these 2 combinations we can see as the 3-sheet aluminum combinations with varying thicknesses. And here we can see that SABC means it is the hot press formed steel with 1.5 gigapascal to the 6451 normal aluminum, and the 980, as you know. And then also we have shown, the cast aluminum things with the hot press hardened steels and all those kind of things. So 1 or 2 combinations how we proceeded we have put over here. These are the attributes which I have shown, and you can see that this is the 9 means the very high edge distance, as you can see over here, which the monitoring data is differing. But one of the things should be noted is that when the edge distance is reducing, the monitoring curve is moving to the right. So then we kind of did some TST. So we can I have just surface analyzed all those kind of all these things, and we can see that as the shear load increased linearly at the beginning, and followed by an yielding period with a large increase and extension, but little increase in loading in here, as you can see over here. Finally, the load gradually drops as the failure occurs. And as the edge distance is increased like this, the stress concentration on the constrained sheet edge was reduced as indicated by the strain distribution, if you can see, and which I have actually checked with the simulation things. And what happens is this allowed the sheet material surrounding the rivets to deform, and at the same time the rivets to tilt further, like I've shown here. There will be a little tilting if you read this. You can see over here, and so what happens is under continued loading from the tensile shear testing, the rivets can become loose and progressively pulled out of the sheets, as you can see over here, and leading to a kind of gradual drop on the load and finally separation like over here. So I did some kind of attribute things, but what I wanted to show, this is the cast aluminum thing. When the edge distance is reduced to much away, this is the top sheet rod and bottom cast. What happens is the HF moves down at the same deforming force of 555 kilonewton, which I have applied over here, and eventually lead to the crack in the edges. So this as well I have kind of did the followed kind of analysis. But what I wanted to show you is that the digital image correlation which I have done using the softwares. So these are the digital image cameras which I've done, and the painting applied it is coming. So basically the DAC is used to see the out of displacement deformation behavior during the lap shear joining. So what happens is that the before this, I think it is better to show the pictures. Yes. What we do is we will kind of paint these things. So the simple dots in between, as you can see over here, these movements can be identified from the software. So the strain development during the movement can be easily caught from the DAC experiments. So moving on, yeah. So this is the load versus testing time and load versus displacement graph which I have shown. I think both are seen. So the time you can see over here as well as the displacement you can see over here. So what happens is that when this is a 0 second and gradually going down to the failure, as you can see over here, what all things we can observe is that you can see how the strain is evolving. So due to the joining zone rotation, the free edges of the sheet, that means these parts experiences. Sorry, give me a second. So you know that there is a bending moment which acts during the testing. So the edges of the sheet experiences a secondary bending, which is higher at the top sheet, as you can see, which actually bends its legs. So the strain is developed in the vicinity of the rivet rivet head, we say. So this leads to the pulling out of the rivet from the bottom. So combined tensile and the shear stress field at the load bearing area eventually results in a pull out failure of the rivet. So the tensile shear component which causes necking around the joint, and further you can see that if the edge distance is too near, like here, what happens is that crack can be developed here, which can eventually reduce the load bearing capacity, which is needed in the automotive circle. So this I just shown sophisticated localized strain which is in the SPR joining. This is in the joining, but this is produced using the Simufact software actually, which I have shown just the edge distance of 7 as well as a 5 millimeter. So how the in the both the cases the strain development is a little different. So this macro image can provide a qualitative representation of the damage observed in the cast and rolled aluminum and the 3-sheet wrought aluminum things. So further, what I have done is that macro image, surface images, and the 3D confocal which I have shown in the previous slide, previous PPT, and the simulation results are combined to understand the effect of the edge distance on, I mean, in the short flanges, how these things done. So we can see that the visible cracks are there and deformations are there, and the 9 millimeter and 6 millimeter, which you can see that a small deformation which you can see over here, which is shown here, which is called as the orange peel effect in the SPR joining process. So to quantify the orange peel effect, we have kind of used the 3D confocal microscopy, and the like the surface profilometry, we will also measure the height variations in the each edge distance things. For example, the 9 millimeter thing over here has shown a height variation of some small 104 micrometer, and whereas the 6 millimeter it is gone. You can see there is a large deviation, and it also shown a height deviation of 270 micrometers. So these things can be measured and quantified and used as a quality criterion. So with this, I'm kind of stopping. We have also identified the critical edge distance in these things, and all the um, other attributes. So I believe you must have enjoyed the presentation, and thank you for listening. I think this session is open for questions.
Dear participants, if anyone having queries, you can ask. The panel is open for the question and answer. If you're having any kind of query and doubts, you can ask Professor. Sir, I have a small query on this.
Okay.
What are the simulations we can do in this? Like, what are the simulation softwares can be applicable for this work?
Oh, in the scanning work, you mean this work?
Yes, sir.
Or
Yes.
generally in the SPR?
I mean, this scanning work, plus generally, like suppose we are using ANSYS for the optimization, like for the simulations or.
Actually, I should have shown some other things. This is one of the automated inline quality inspection systems. Thank you for the question. I'll answer after this. This is our lab thing. Actually, I'll just show you how this is. This must have been much better thing. So this is the automation which we are using for different things.
Everything happening through machine learning or automatically it's happening like how?
No. This is I'll show you that part. Actually, this is our scanning
Scanner.
Yeah, scanner. Okay. We scan the this is the
prototype.
original. You can
Prototype
see.
is there. Yeah. Okay.
Actually, this is the original body invite from a car. We just taken it out, and we will scan all the things, and then you can see that.
Yeah, based on the result, it's showing the results.
Yeah, you can see. This is scanned, and from here, this is all. This is the Polywork software which I am mentioning about, and after this, all other things are our in-house developed thing, which is machine learned, and this is actually the RSW classification, not relevant to our SPR. However, like similar way, we will develop we'll identify different field variables, and we will do the field variables. Like, the machine learning requires a lot of data, and we produce a lot of data and machine learned the defects to classify the defects. And further, what we do is we kind of surface profiling of the things we are done by the software, and then calculate each indexes. And based on those indexes, as you know, this is the STL file, which or the .pc file, which can be put on here, and that will automatically develop the part which you have seen. And from this, spot visualization will be done from the software, because that is required to check where all are the welding happen. And after this spot visualization, each spot quality kind of checked like this. So here you can see that this is a 114th joint or something like that in this one, and identifies each the things. What is the fault? Weld fault is there. The gun tilting is there. However, this is okay. It is within the quality. And edge weld, which I have taken now, all these kind of things are there. This is the in-house developed ones. In the SPR case, however, what I have seen is that majorly we cannot do any kind of, it's extremely difficult to do any ANSYS or abacus things, because the one is the unavailability of data, other is the theories are all based on the both cutting as well as the deformation. Combination is a little difficult. So what we normally use is the Sorpa software or the Simofact software. But from my experience, the results are not that promising. We can publish papers. However, the practicality is a little down from my experience. So majorly, sir, I will recommend to use Sorpa software, which is very simple. Is that answers?
Yeah, thank you, sir, for your nice answer. But that's what you're recommending, Sorpo software. That is only relevant for this kind of work and for better result and all the things.
Yeah.
So in that, every data will be automatically give you as output from that kind of things.
Oh yes, this software very well gives.
Okay. Okay, sir. Thank you.
Thank you for your question.
Any other participants are having query? Please, you can feel free to ask questions.
Yeah.
My question is regarding the simulation. Any simulation start with this?
Doctor, can you speak up? I can't listen.
Dr. Ahmed, please wait. Let Manish Kumar complete, then you can start. Dr. Ahmed, please wait. Let Manish Kumar complete, you can start, please.
So myself, Dr. Manish, working in CPET Jaipur as assistant professor.
Oh, hello, professor.
So my question is that nowadays we are a lot of talking about data, and also when we are dealing with the simulation, all simulation, especially in mechanical, start with the discretization, which generate huge data and require boundary conditions. Yes. So that now we can directly automate the things to apply boundary condition, all those boundary condition, initial conditions.
Yeah, right. You are right. Or if the data is less, there are methods to increase. Means we can produce more data using the modern machine learning techniques. We can make a confusion matrix or something like that. That's what you are telling, right?
No, my thing is this: you see, in simulation we required a lot of iterations to produce to convert any data.
Oh yes.
So that
That's
it can
true.
be done by the AI or machine learning kinds of stuff.
Yeah. Is that the question? Sorry, sir. Was that a question actually? Hello, sir.
My question is that people are so the data is the crunch of the 4.0 industry or AI, machine learning, anything we take, and also in simulation we required huge data, it generate huge data. So say we can use directly AI in simulation without human intervention.
Yeah. Professor, so the say for example, we can put a lot of data, make the simulation. We can do the automation, something like this in this stage, right? From my PPT, right?
Yes, sir. Yes, sir.
Yeah. However, the problem which we encounter is I will do one thing. I have another PPT so that it will be more easy. The problem is, Professor, this all gives the quality analysis before welding. So do you understand? It can predict, oh, this is this much tilted, or this is similar. So it can say that, oh, this is this, right? But
Yes, sir.
What if we need a online there itself monitoring, which will be better? Will that be a predictive equation or really getting the real-time thing? See, we are not doing the non-destructive things just because the problem is we are not getting the real-time monitoring data, right? Because here what we are doing, as I have seen in the shown in the video, what we are doing is we are measuring the real-time video. See, sir, these are the some of the SPR field variables given in the literature, which they have just made from the I think the laboratory. So I can also show these you can look at. See, these are some of the SPR issues. 1, 2, 3, all those kind of things. I really do not think that any kind of AI before joining can predict some of these problems. Do you get me? So that's why, yeah, that's why. See, for example, this kind of large issues, yes, maybe it will be extremely difficult to predict using the AI. Kind of, this is a no flaring issue. Outside, you can see this looks perfectly all right. So I believe that a combination of the original 3D scanned data and original monitoring data, which I have shown in the second PPT, that gives some of the characteristics which I haven't clearly explained due to the time constraints. I think real time monitoring with very high speed may be the right solution, it seems. Oh, is that all right, doctor? Does that answer?
Thank you, sir.
Oh, thank you, sir.
Sir, I request to please share this slide. It is very good, insightful information. If you note the confidential, if you don't have any confidential slide.
I think Professor Zubair is having the video that will do, it seems.
Okay, sir.
Hello, sir.
Good evening, Dr. Ahmed.
Dr. R. Ahmed is speaking from Sabu Siddhi College of Engineering, Mumbai. So just you mentioned the name of software machine learning, I mean, to check the quality of welding.
Yeah.
So what's the name of the software?
Oh, that is the in-house developed software, Professor, which I have shown, which is available in the, we can see over here.
Thank you, sir.
You can just copy down.
Thank you.
This is my professor actually. Okay.
Participant, if you have any question, please ask. Doctor, what about the simulation sampling? You did some, I think, so many simulation in that one. So these are all SimuFact or some other software?
The softwares here what we used are SimuFact softwares, but the thing is that we have collaborated with Hexagon and then all in-house developed things as per our data, and we have kind of collaborated and produced all the edge distance things which you can see. But these things are not this can be easily done. The orange peel effect things and all are kind of we have collaborated with Hexagon and then done the things. All are SimuFact.
Sir, for this resistive type welding, normally what kind of heat source we have to use?
Resistance welding, you mean?
Yeah, for resistance welding, what kind of heat source we have to use? Normally for TIG welding, we preferred Goldleg double cycle model.
You mean the
Heat
machine?
source. Heat source.
That word I am not getting. Sorry.
For modeling the heat source, normally for TIG welding.
Heat source. Oh, you mean
yes.
heat source.